Hello, hello. Hello, hello.
Yeah. So yeah, there's lunch after this. Video work again?
Seems to be okay.
Oh yeah, okay. Mic is on. Going to other. Oh no. That's right.
Am I me? Can you confirm if I'm me? I think I am.
Yep. No, really tired. So yeah, I can add a halfway timer too. So that will be at around. I want to set an alarm on my phone, which is bad. I can also type a message here and it will.
Yep.
Type a message here and so. Now hopefully it will not turn off. That was an app. Because an Android you can only set it alive up to half an hour. Just keep down, you need an app. You set the system setting.
I think it's almost proper Cambridge time of 5 minutes past the official start times.
Yeah, I think everybody.
I think we've got everyone.
Oh, so that's I.
Do you want to do an introduction or you?
Yeah, it's just fun. So hello everybody. Thank you for coming to this talk. It's Andrew Turner and he will talk about 10 years of ARM on FreeBSD. Enjoy.
So I will be talking on 10-ish years, but it's 10-ish because I'm not quite sure. I've got a question of when did FreeBSD ARM64 actually start? It's some of these numbers, obviously, they're different times, points in time, and I'm not entirely sure exactly how you define the start of a porting FreeBSD to ARM64. So I'm going to sort of go through some of these and give a wee bit of a history on them. So I'm going to start with the journey of, think back to about 2012. ARM has just announced the new architecture. And we're trying to explore how does this architecture actually work. So how do you understand the architecture? Or you can read about it. Documentation is always nice, but there may not be. You may have issues, and hopefully there's some source code that you could also read if other projects, similar projects have been released. And you can always write something. Of course, you need a toolchain, and you need something to actually run the code you write on. So we're going to do some reading about it. If you're ever looking at the ARM architecture, you'll find I don't know how many tens of thousands of page document it is now called the ARM Architecture Reference Manual. It's the ARM if you see that. The issue is, I mentioned they announced this in 2012, and the first release of this is 2013. So reading documentation is good if there is documentation to read. The other source of documentation of things I can read is there were patches at the time released for Linux, but you may have noticed there's a thing called the GPL, and we've got the BSD license, and they're not exactly compatible. So we've got to be a wee bit careful doing that. You don't want to accidentally copy some GPL code into a BSD program and have it suddenly have to figure out what the license on that is. It'd be much easier to just do everything clean. So it was possible early on. It was a bit difficult to read things, but it was a wee bit difficult. The other luckily they had, ARM did release GCC and binutils patches. So I had a toolchain at least. I could try writing something and see what happens. This turned out to be the main way I was doing a lot of my early work. And in late 2012, they did release what they call the foundation model, which was a very fixed platform with fixed hardware. It comes from a product this is a specific version of what's called the fixed virtual platform, which is a slightly more complicated tool, which comes from the fast models, which is a very complicated tool, which various companies use to test hardware before they have hardware. So I could use that to at least try running something, see what happens. And luckily, there's a Linux boot wrapper, which was BSD licensed. It still exists. It's still used in various things. But so I could modify that, and I didn't need to boot into a BSD-like thing. Into Linux, I could boot into a BSD-like thing. And it was used just to get the model into a known state where I can do whatever I need to do. So I sort of, early on, get these two tools, get these tools together, figure out, and then use this to figure out how do you create, how do you actually create something? So I created this project, the ARch64 FreeBSD sandbox. And this is one of the possibilities of what we consider the start date. It still exists. I haven't touched it in over 10 years. So if someone really wants to see what old code looks like, it's still there. So the first piece of code that runs in the kernel is in a file called lowcore.s. And this was the first attempt at writing this. And there is some of this code still exists in FreeBSD. It still exists in FreeBSD. I have renamed some of the things, and some of the bits have been changed. And it looks like OpenBSD has some as well, where I think they took some of the FreeBSD code early on and reused it, and they've gone in their direction as well and changed things. So that may be the first date, the start of FreeBSD ARM64. But this is now getting the boot wrapper runs in what's called exception level 3, which is the highest privilege level on ARM, on ARMv8. And it's not normally somewhere where the kernel runs. So it just gets you into one of the lower exception levels, called normally EL2, that's more like imagine it's the hypervisor level. That's where you typically run the hypervisor. That's where the kernel would have entered at the time. And then we then have to drop down to EL1 to run the actual kernel. And so EL1 is the kernel level, EL0 is user space. So what we do is we need to do a little bit more configuration. And so this is me trying to figure out what this configuration is, write the assembly that would do this, and get into EL1, where we can then do things like build page tables so we can turn on the MMU. There's still got the problem of no documentation of how any of this should work. I think I had might have been some instruction lists, so at least tell you what they do, but nothing on how the page tables are laid out. So that's where looking at Linux was about the only thing I could do for that. So the way FreeBSD boots is we assume the MMU is off, or MMU is either on, but with an ID map, so every virtual address is the same as a physical address, or is off. In the early case, we just assumed off because that's what the boot wrapper does. There were no documentation, as I said, so looked at Linux. But luckily, ARM added a nice instruction called address translate. So what you do is you give it a virtual address, you run it through this instruction, and you read a special register, which gives you the result. And that will tell you probably messed something up. And hopefully, it'll give you some information about why you messed up. So it tells you, it says, are you, this level of page table walk is unmapped. There's nothing, it's an invalid mapping or something like that. And you then go through, you figure out why, essentially. When turning on the page, when turning on the MMU as well, you've got the problem in that the MMU's on, and that includes for your code. So what I often had to do was I was running on EL1, which is the kernel level, taking the exception to the hypervisor level, and then try to figure out what just went wrong. That sort of worked. I got most of the way through page table creation. I did time passes. I moved to the UK. This has all started originally when I was a developer in New Zealand. I was going to give a talk in Malta, BSDCon, EuroBSDCon 13, and it was about something. It was about ARM. Obviously, I do ARM things. I was going to, and I saw Andrew Wuffer was there. He's going from ARM. I was going to ask him about documentation. And then they released it 3 weeks before the conference. So luckily, I didn't actually have to ask him in the end. I got that. So we can go, yay, I've got documentation. And there's an access flag. If you don't set this flag, all access is trapped to the kernel. That was my problem. And if you don't set this in the kernel, all access is trapped to the kernel. And then you have an access which traps to the kernel. As you can imagine, this is why you can have some issues with this one. So set this flag, and everything works. So possibility two. I've done this. We've got the MMU working. At least I've got some C. Always had some C code running there. MMU may be off. We load it a known virtual physical address, so we can just build it as a static binary. Turns out there's more than just the startup code assembly in the FreeBSD kernel, and so we can move. I was moved to a Subversion project branch because this was well before our migration to Git. So yeah, FreeBSD is more than just locale.s. That's shocking, I know. So February 2014, I created a project's 64 branch that was starting to think, well, okay, we've got something we can get into C. Why don't we try actually doing all the other bits that need to get into, we need to get FreeBSD running. We started with, we need a toolchain. Luckily, up until this point, I'd be using GCC and binutils. Luckily, Clang had added support in 3.3. Unluckily, we still needed to use binutils. We didn't quite have a linker, I don't think, until much later. And also unluckily, this was quite buggy. This was the first release with LLVM. And luckily, they did improve in later versions, and so we've got. I was looking at some of the old changes, and there's some of the later ones were remove a workaround for LLVM 3.3. Something was broken. By this stage, there was at least a bootloader, slightly better boot strategy than just run this random command, this set of commands to get you into the state you want. It was now actually some boot firmware, so ETK2, we could use EFI booting. U-boot hadn't been ported, I don't even think, to ARM64 at the stage, and definitely didn't have EFI support. The problem is the way that we built loader.efi is build an ELF file. This is on AMD64. Build an ELF file with. Tell it, occasionally we have to tell it they use a slightly different calling convention because they use the Microsoft calling convention. We don't have that problem, luckily, on ARM64. And then use object copy to create an EFI file. We still don't, as far as I can tell, have object copy to build an EFI file. we do this. If you don't recognize, this is some assembly that says, build me a PE cough header manually. We do have some macros at least to say this is a ARM64 machine, and you can do some basic arithmetic to give it offsets of things. What we have to do is build an ELF file and object copy it to a binary, and this header magically appears at the start of the binary due to a linker script. And so when you do that, you actually get a proper EFI file. It's a bit of a pain to do but once you've done it once, it's fine. I will point out this was inspired by Linux. They do something similar with they can boot the kernel as an EFI file. So I did a port of loader. There were some cleanups there. It's a lot nicer nowadays than it was at the time. But still, the kernel's still more than local.s. I still have problems with all these things other than it's not startup code. What do you need to just build the simplest possible kernel? There's lots of functions that are machine dependent that you just have to have on every architecture. They may look slightly different on different architectures, things like copying from user space to the kernel. You're probably going to want to write that in assembly because if you fault in the middle of that, you want to unwind everything. Or you have to check ahead of time that you're not going to fault. So how about we just implement everything as panic and we'll deal with it later. That was the strategy I tended to use. And the other problem is you may not know where, when you're trying to actually get into C code, or you may not be able to know where you are in the boot process. So having something like this assembly to do a put char, say, I'm here, come and get me, come and fix me. That was also useful. So I do this and build a kernel, try it, run it, find it doesn't work, figure out why it doesn't work. This is just a big iterative process. But after a while, you get to the first C instruction. Yay! We're in, well, whichever function. On AMD64, they call it hammer time because I think it was the first hardware was the hammer. Or there's something early on that was called the hammer. We just called it in ARM on ARM. I couldn't come up with a fun name. Yeah, so we definitely more than just local.s. You need to do a few things though in C. You can't just start running code, your machine independent code. You pass data. There's some data gets passed from the loader to user space to the kernel. Things like your DTP, or ACPI tables now. But at the time, it was just that. You need to pass in physical memory locations. So we need to know whereabouts to actually assume memory is, because we don't know, we don't happen to know. We ask EFI and loader.EFI, and then that will tell us. So you need to do that. You need to do some bootstrapping. You can do some of that in assembly. It's a lot nicer if you can do it in C though. You need to turn on the console. It's nice to have printf running, working. There's a few things like proc0, which is the kernel process in the initial thread. And there's a few functions, random tuning functions. You just call and you just pretend you know what they do. You don't actually, it doesn't particularly matter. It's just called early on. And luckily, once you've done this, you can enter machine independent code. And you find pretty quickly you need to actually do more virtual memory. This is just a story of virtual memory, I think. There's a layer of machine-dependent code called PMAP. This is what translates, that's what creates page tables. So it's asked to say, you have the virtual memory management code that goes and asks PMAP to say, create me this mapping, or tell me some information about this mapping, or things like that. I thought, AMD64 looks really complicated. I'll try writing my own to see if it can do it simpler. You do that, and you fold in a few more instructions, and eventually you get to this thing and say, oh, I can get to mount root. I managed to boot the whole kernel. But then you realize there's a reason for complexity. PMAP's really complex, even if you write your own. You just start and then you think, okay, I'll try something. I'll try reusing AMD64s. And userland just magically works. You get into, it's complex for a reason. For a long time, it took me I was saying, why is I had to get my head into this. It took me a day just to get back into PMAP, looking at PMAP code. But eventually you get to userland, and then you've got the problem. What userland? You've got to actually write all of this suddenly. So you've got a few things. So the very first code you get in the static binary is a thing called CSU, so the C support utilities, something like that. It means something, I'm sure. libc is fairly important, and eventually you want the runtime linker, so if you want dynamic binaries. CSU's first code, it could be run, there's a couple ways. It's directly loaded from the kernel, if it's a static binary, or via RTO, the runtime linker, if it's a dynamic. It does load argv-argc. It's not just magically put into by the kernel. They're stored on the stack, and then you have to find them. And there's a few things like init and fini, which are old ways of doing pre-main and post-exit or on-exit handling that we needed. It tends not to be used nowadays. But you still need them just in case you've got some old toolchain that uses it. And you need to do both sides of syscalls. So luckily, FreeBSD just generates them from syscall.master, but you still need to tell it how do you do a system call. And long jump, set jump, there's a few misc functions here as well. And then you get into init. So maybe this is the start. We've actually now running C code, user space. And luckily, around this time, I got made redundant, which is great because FreeBSD Foundation said, we've got some money. Do you want to have it? Well, not all of it, obviously. They wanted some. And Semi-Half as well, who's a consulting company in Poland. Poland. So we did this project to actually make FreeBSD 64 a real thing, not just. I think at the time I was building partway through. I think the instruction would say start building, use this build world, but you probably won't get the whole way through. Doesn't matter. You only want a few bits of it anyway, and so we wanted to actually be able to build everything. So we did. There were 3 parts. There were 3 parts we did mostly simultaneously. We did some more kernel bring up, so other part, we didn't just, I guess, got the minimum to work. We wanted to actually get something usable by more hardware. We did more user space bring up so we could actually run the whole user space. And there was also, we used the ThunderX as a reference platform because some of it was funded by Cavium, who built ThunderX. So this was about 2014. So this was almost 10 years ago, so maybe this is, if I'm saying 10 years of FreeBSD ARM64, this would be the right date. And this was also the first time someone paid me to work on FreeBSD, so everything up to this point was just evenings and weekends. So this was all done in the FreeBSD Foundation GitHub. So there's a branch in there, there's a few branches in there. One's, I think it's an ARM64 branch, if you want to have a look at old code and how the process we were going through. I was mostly faulting in these functions that I just implemented as panic, and as I kept finding new functions to implement, I'd handle them. Both the user space and the kernel. So working on getting more of the kernel implemented and more of user space implemented. And we had an ARM64 to do comments, and I think we may still have a few of them around. There might be in some weird obscure corner cases that I think I saw an ARM to do panic actually when I was doing a grep for them recently in some obscure corner case which we must not hit. So semi-half, I think they focused more on ThunderX. So it was useful for that in that it was actual hardware and it implements things that the model may not. I was working on the ARM model at the time. So we did, floating point, gigv3, DDB. That was gigv3 and DDB, I think it was semi-half. We renamed to AR64 because software expected that. And we were building with Clang. I think we still definitely needed external bin utils. And then that project went well. So maybe, is this the start of ARM64? This was importing the kernel. It wasn't the first ARM64 change in the tree, but this was bring in the kernel. Okay, we can now, there were a few more changes after that, obviously, and user space had to come in as well. But should we consider this? Could we consider this the start? But as I said, we did make some decisions. We have to make some decisions when doing this. We need to boot with, need to boot with UEFI initially, just because it's so much easier to have someone else deal with the early boot things. And we don't need to worry too much about dealing with having to figure out what mode are we in when we enter the kernel. We did CPU start with a tool called a thing called PSCI, which is a way of calling into EL3 to ask it to do things, to do power management for us. So they would do CPU on. There's another method called spin tables where all the CPUs are running and everything that's not the boot CPU is just spinning on waiting for you to write to a specific piece of memory to tell it where to jump to in physical memory. The issue is that it doesn't give you any feedback as did it actually work. So I ignored that to begin with. That's now, those two are both being changed now. We can build a boot I image to pretend to be Linux and boot from U-boot, and you can use spin tables. We only targeted FTT, so you assumed you had a DTB. We fixed that fairly early on to also support ACPI because FTTs common in the consumer devices, in your mobile phone type devices, but ACPI is preferred in servers. So, those top three have all been, there was some early decisions we made, but they've been changed since then. And as I said, I implemented functions as needed. That makes things so much easier not to have to do everything all at once. Hit them as you hit things, figure out how do you actually implement this? How do you test this? Because if I just go and write everything, I don't know, am I actually hitting this? Is this going to work if I do hit it? Yeah, as I said, I did a wee bit more project for the foundation. We wanted to expand virtual address space to 48 bits. Everything on ThunderX was cache coherent. So DMA was all cache coherent, all the devices. We didn't have to worry about forcing everything out to RAM because the device you're talking to doesn't talk to the cache. Since when we started this, I wrote a simple IRQ handling framework. Since then, Intra-NG moved into the tree and became sort of machine independent. It was ARM and MIPS, I think, were the first two. So we did we updated the drivers to work with, and ARM64 to work with that. We did some super pages. So these are, if you've got a 4K base page, you can put together, and you've got them all, and you allocate your physical address space in the right way, you can put those together into a 2 meg super page, and it reduces TLB usage and ACPI. So we need a few things for into NG. We'd brought in GigV2 driver was already supported, and we just needed to do the GigV3. We needed to support MSI and MSIX interrupts because we've got PCI, and so we needed to pass the range. And the way the GigV3 works is there's a separate thing that normally handles. There's another thing called the ITS, which handles just handles MSI and MSIX interrupts. And eventually we could just remove my old code. It was sort of probably the best idea. And I said super pages, we did that. The issue you've got with super pages in ARM64 is we have a thing called a break before make sequence. So you have to remove the old entry, do a TLB invalidate, create the new entry. What happens if another CPU accesses that entry, that virtual address at the wrong time? Hopefully you can do this quickly enough. That's very rare, but it's going to happen, so we've got to handle that. What we do is we just enter the kernel, enter the exception handler, check, does this entry actually exist now? And if so, just return, because we're probably in that sequence. And there's lots of issues with this in the kernel, which we have fixed, luckily. So we disable it in the kernel, just because until you find them all, it's very difficult. So, first release, was that the start of FreeBSD? I think this is probably getting a little bit too late at this point. We're saying, yeah, releases a wee bit a bit late for saying the start of something. That's the start of something other people can use in an easily usable format, maybe. So our first release was FreeBSD 11. It was prior to this, we'd originally put in sbreak and break calls and decided they'd been removed from POSIX years before, before ARM64 was a thing. Do we really need these? Emacs seem to not like that, because there's an email here at 30 saying that when told that these had been removed, they said, "Are they mad?" So I think that's as a Vim user of Vim, I think that's a badge of honor. I considered, yeah.
Could you implement it based on mmap in user space?
They did something. So the question is, could we do an mmap in user space? They were using sbreak, I think, was to find the end of code. So my understanding is that the way Emacs was worked is when you built it, they intentionally crashed it to create a core file, and then used sbreak and break to load it, to get some address to load the core file back in. To basically, rather than having to do some expensive startup, they could just load the data once. So we could implement those with mmap, sbreak and break with mmap. It would still break Emacs, though, I think, because of how they're using it. So we have discussed in the past, and I think Brooks has suggested we do maybe have a library for this that does, if people want it, implements it, sbreak and break using mmap. Or maybe we just have one that returns the failure every time, or in our case, just not have it. So I consider FreeBSD 11 was a nice technology preview, but it was not the best. This was only we hadn't spent much time on any polish on this. It was more of throw the code into the repo, see what happens. So yeah, Float 12 was a couple of years later. We could support, if you want to do anything like, say, kernel crypto, someone like, say, Netflix, uses this sort of thing in some of their models where they want to encrypt data before sending it out on the network. So you may want to be able to do kernel crypto for this. But that the ARM64 instructions assume you've got floating point enabled. They want to be able to operate on floating point instructions. So we needed to get AES support, we needed floating point in the kernel. There was, luckily, AMD64 support, and it's just translate that to make that, I think it might have been PowerPC as well, just make that look ARM64-like, and sort of mostly just worked. This was when we had ACPI come in. So you could build it, you could run on your servers. We did PAN, which is by default, the kernel has enough privilege to be able to read all memory in the system. What PAN does is says, if user space has write access to this address, we want to disable, when we have PAN enabled, we disable privileged access, so the kernel can't access that memory. That is great, except one case of execute-only memory, which we don't have. So basically, it stops you, it catches a lot of bugs of doing mem copy rather than copy in. If you're writing kernel code and you just mem copy user space memory, that will fail if you've got PAN, which essentially all modern hardware will have. We execute never, so make sure your data is non-executable. We did some early NUMA, there's some EFI runtime services, and I think there was like the early Linux data was in there as well. So running Linux binaries on FreeBSD, user space binaries. And then we'd done enough work. We got tier 1 and managed and demoted i386 Link to tier 2. So we still only have 2 tier 1 platforms. We wrote I think it was Olivier or someone wrote Combat 32. So you can run ARMv7 binaries on ARM64. You definitely can't run ARMv4 and 5. You might be able to get ARMv6 if you're lucky. I haven't tried it.
It does work, but the kernel only advertises ARMv7.
So the answer is that ARMv6 does work, but the kernel only advertises ARMv7, which, given I've just removed ARMv6, is probably I have no problem with. We did some there's some ACPI updates. There's some GigV3 driver updates. There's always PMAP update improvements. We managed to get finally got super pages working in the kernel. There's some issues around making sure that your exception entry point doesn't hit you don't promote the memory that the exception entry point needs to access to be able to handle the exception. Because of the same issue is you'll get an exception, and then in your exception handler, you'll get an exception. And in your exception handler, you'll get an exception. Johnson did LSC atomics. So these are atomics on ARM64 is pure ARMv8.0 is load exclusive, do some operation, store exclusive. If that memory is being touched, the store exclusive will fail. LSC atomics say do certain operations atomically in a single instruction. So it can have a load and store in a single instruction. And we did some booti. We got booti support. So this was booting. We can build the kernel as a Linux image and boot it from that. I did a per thread stack canary. So FreeBSD kernel has stack canaries, but on ARM64, there's a single stack canary for the entire kernel. So you could potentially have cross-threaded attacks that way. ARM64, we have a single stack. Each thread has its own canary, so you have to figure out what it is per thread, not globally. I did pointer authentication, so when you enter a function, it will sign. It can sign the stack pointer, and then signs based on stack pointer and link register the return address. And then on exit, it will authenticate that and either raise an exception or.
Do we have any user space software that actually uses that?
User space software, I'm not sure if we enable it. We do enable it in user space now. Yeah, everything in the base system has it enabled. Another question?
Does the 16K page size effectively provide a new API?
So does the 16K page size effectively provide a new API? Yes, if you're assuming page size macro is a static thing. There is a function to ask the page size you're running. We've mostly got rid of the page size use from the kernel, from user space, except malloc. JE malloc is the pain because it needs to hard code it for JE malloc reasons.
We also added code there.
And I am slowly working on trying to remove page size macro from visibility from user space. But there's a few other things around pipes and a few other libraries that need it. I think this is when we got some initial Azure support, and we actually now allow spin tables. And SCMI, initial SCMI patches, which is a way of talking to some management hardware. And if you're interested in that, there's a talk tomorrow on further work on SCMI. More improvements. And also, there should be 15, sorry. This is so we have SCMI improvements, which will the talk be on. Random number provider, BTI, which is when you jump into a function, it has to be on a specific instruction. You can't just jump into the middle of a function. We find that we've got Beehive support. So if most of your ARM hardware, except for Ampere Emag, should just work. Ampere Emag is known to be buggy, or FreeBSD on Ampere Emag is known to be buggy. There is both using ARM v8.0, which you go to the hypervisor and back out, and VHE, where you run the kernel in the hypervisor level, so it should be quicker. We did watch points. We added watch point, and we're adding hardware trace. That's something Ruslan's working on, and we've got Zachary Lee from ARM has done SPE support, the statistical profiling. So it will statistically sample instructions to find and give you information about execution time. So it can be useful for finding where you've got a loop of code that's running regularly that's slow. And Ruslan added the core site with hardware trace. And almost have SVE, which is take neon or the floating point and just make the registers much bigger. And basically a multiple of 128 bits. But it's hardware sized, and we do get some choice on software and to reduce the size if we want. But it's big. It tends to be bigger bigger registers. So in theory, it should be. It helps in some cases, some situations. But I couldn't tell you what because I'm a kernel engineer and I don't do floating point, except in very specific cases. I expect to start MTE soon. So if you, but also looking in future direction on what people. So MTE is tagging pointers for deterministic. It's kind of a SAN-like thing in hardware. But we're also looking at future directions of what people are interested in the current architecture. So when did it start? I don't know. Sometime 10-ish years ago. One of these dates, maybe, none of them, somewhere in between. I will leave it up to everyone to decide. And I'd like to thank a few people. The FreeBSD Foundation, they organised a lot of the early work of doing this and getting things working. And the University of Cambridge Computer Lab for running basically the Morale project. So telling Robert Watson there, employing me to make this more production ready. You know, just work on this, get things ready for Morale when it starts. And if you haven't worked out, they now employ me. I'm now a software engineer there, working on the kernel. But they also have they funded some of the work through the foundation. And so, yeah, thank you. Are there any questions other than, yeah?
How far out do you think you are for ARMv9 and SV2 support?
ARMv9, SV2, well, ARMv9 should just work because it's compatible with ARMv8. SV2, I had a look. I don't think there's any new, everything's just new instructions as far as I can tell. So unless I'm missing something, then it should just work once we get SVE, because it's just some hardware caps to tell the user space that's there. Yeah?
Is anyone working on GIC-v2 support in Beehive?
The
Interrupt controller.
what, sorry?
You can do something like a Raspberry Pi with Beehive and other SPCs, which still use it.
The GigV2. I added support for it means that we don't just have GigV3, but I have not done GigV2 support. I looked at that and I thought if someone really wants to, they can do it. I prefer not to touch it. But I don't know of anyone that has plans to do GigV2. Yeah?
What's the current timeline for the continuation of AH32 support?
I
Contentious topic.
so there's questions on timeline of AH32. I couldn't comment on any future decisions. Mostly I don't know. Yeah. Questions on IOMMU, anything about it? We were looking at cleaning up some things. It mostly works except we need to handle MSI interrupts from it. Because Ampere Ultra has an MSI rather than a normal interrupt. So I think that's probably the only thing that's missing from that. So if you want to implement that, I'll be happy. It means I don't have to. Yeah? So power saving, yeah. Anything about it? So there's some ACPI power saving things, which I don't remember exactly what the acronym was off the top of my head. I can add it to my list of things to look at. I don't think we have it. We haven't had time to look at it just yet. I have got last question on my screen here.
It's a list of known working boards you can source.
Is there a list of known working boards? The FreeBSD wiki has a list of boards. Whether they're working or not in the current version, Raspberry Pi 4? Yep, thank you. I think we've run out of time, unfortunately. If you've got any more questions, I will be around.
Well, I can. Right now it'll be 10 minutes instead of 30 seconds. That should be a bit better. The timer? Yeah. It's not rolling yet. I should probably plug in, huh? Okay. Now. If I put it in mode in like. I was trying to get it to mirror, but I can't get it to work. F11.
It's a familiar IP address. Okay. You ready?
Yeah, I think.
Good afternoon, everybody. After lunch, everybody awake? Good. It's always horrible being after lunch, I find. So I wanna welcome Patrick Marchand. Did I pronounce your name correct?
Yes.
Perfect. Awesome.
Mostly.
So the first OpenBSD talk, we don't count Henning because that was not really an OpenBSD talk of the day and of the event. So Patrick, thank you.
Hello. Well, it's an OpenBSD Lite talk. It's mostly OpenBSD as a user than an actual developer story. So the title of the talk is Puffy Does Real-Time Hypermedia. Nowadays, modern web development implies a lot of JavaScript in about every interaction. People even use it on the backend nowadays. This has led to complexity, too much complexity, I don't know. But I think there's more than one way to build a web app, and I'd like to explore some of them with you, and maybe show you libraries that I've started using and contributing to. This is an actual website, so if you go on the link there, you'll be able to follow the presentation along. There is one of the slides is actually interactive, so. Right. So, who am I? I'm Patrick Marchand. I used to be a system administrator doing Debian and OpenBSD work for a French company in Marseille. But I come from Quebec. In Montreal is where I live, but I come from Tremblant, a little bit more up north. I also worked as a ski instructor for 12 years. And I have a lot of other hobbies that we can talk about during the breaks. I worked as a for-hire programmer, so and I currently don't have any hours free, but soon maybe. So what is hypermedia? Hypermedia, well, this presentation is hypermedia. The web is hypermedia, and arguably one of the most successful ones out there. It's basically just, you have links between the documents, and these links are contained often inside the documents. These documents can be of a variety of formats. They can be video, audio, text, and these links between, by linking between each other, you can traverse them easily. And at the beginning, they did tend to be relatively static, and when it's video, audio, these are usually static. But since the links are simply addresses to content, the content behind them can change. And this has been used to great effect in the first type of major web applications we've seen that are multi-page applications. These MPAs have a backend that is done written in any language you wish, and a front end that is usually just HTML that is being sent to the user. With time, people have wanted to have a little bit more interaction with the pages, so we got JavaScript, and for a time, Flash. The Flash was, well, that went away. It was very insecure. With multi-page applications, to modify the state on a website, the user inputs information into a form, then sends that to the backend, processes it, and then sends it back to the user with an updated state. What transits between the server and the user is HTML. The browser needs to redraw the page with the new HTML every time to be able to show it, and that means that we end up with the infamous page blip. And JavaScript is what people have been using to get rid of that infamous page blip. It's gone through many forms. Different libraries have come and gone. The big one I remember was jQuery, where you could use CSS selectors to navigate your DOM in JavaScript and do modifications on it that way. It's pretty useful. But there are limits to this kind of model. There are certain apps that are hard to do in it, like interactive maps or video games. And this is where the next type of application came into being. Single page applications. So they're a response to a multitude of things. The page blip, interaction times that could be relatively slow when you have to change pages. And also people who had a lot of state transitions, a lot of animated state transitions like you can have on a map where you zoom out, zoom in, or applications that have a lot of documents like email clients, where sometimes you'll want to flip between documents very rapidly. This is where people have reached to a new kind of architecture called single page applications, where we'll see that most of the state is handled on the client by JavaScript. And we've had large frameworks that were born to support that. Stuff like React, Vue, Next, which uses React, I think. These big frameworks, they replace a lot of the browser APIs, a lot of the native browser interactions. So like stuff like routing, form handling, and a few other things. This means that they needed to recreate their own code. We ended up with like basically native style applications on the browser instead of the old style of hypermedia applications where everything's dictated by HTML. And when you do a request to a link, you receive new HTML that instructs you how to further interact with the page. Having to rebuild a lot of the base browser features, it complexifies the code. So when you and it also makes the code base bigger. And so these clients that receive that have to download this HTML can sometimes be stuck in long load times for the initial page load. Solutions have come out to handle that, such as tree shaking and bundling, and minifying. So these are minifying will reduce they'll take all the variables, get them as small, get the actual string size of the variables to be as small as possible. So let's say a variable list of objects becomes LO, and so on and so forth. And then they send that minified code to the client. Tree shaking is just you get rid of all the code that isn't being used by any function in your application. And other tricks like this, these tools are very useful, but they do complexify the programming process. And with time, the developer experience with JavaScript has become a lot more complicated, but it has also improved. To handle this complexity, we also saw the creation of TypeScript, which is a static version of JavaScript where the codes are defined in advance, and there's a transformation of the TypeScript code to JavaScript before it's sent to the browser. That has also complexified the dev experience, although probably for the better in most cases. I'm not 100% sure that static types were the best solution for a dynamic language like JavaScript. Personally, I feel like a mechanism like design by contract with contracts that you can put before and after a function and its signature are maybe a better fit for bringing assurance to dynamic languages. If you want a good example of that, you can go look at AFL lang, but that's a whole presentation in itself and a whole other can of beans. And since I've been here for a week, so I'm pretty full of beans. One thing I've seen a lot working with single page applications is that since you often have like a backend that is completely separate that needs to be JSON, that needs to speak JSON, you often see people filtering that JSON on the client. Now this is okay for some information, but if that information is sensible, it can get dangerous. You never know, and you never really know how people are going to use the information you give them. They can abuse systems in ways that you would never expect. So it's better to send only the information that the person needs for their interaction with the application. And I find the silo between back-end and front-end that you find in single-page application, it does tend to encourage that sort of situation, especially when you don't have any dedicated people on the backend team, which honestly tends to be what happens in most of the projects I've ended up working in. And so it's only mostly front-end people who know a little bit about programming backends and will just do the simplest possible to get it in their JavaScript environment where they're most comfortable, and then do the filtering. Also, since the backend, it's a whole other app in itself. Now you have two different applications to serve one need. And most companies I've seen don't actually have more than one client for their backend. So they've got a lot of code duplication that's not necessarily necessary. And I think a lot of people would be probably better served by having a well-documented modular backend that can directly serve HTML than doing this kind of siloing. I did want to talk quickly about some prior art on the subject of BSD web development. Kristaps Johnson's, not sure if I'm pronouncing it correctly. He did BCHS stack, which is he uses OpenBSD, HTTPD, SQLite, and C to build his applications. And he's built a lot of helper programs and scripts to simplify the process of working with these technologies and building apps. His tools can be used to build multi-page applications or single-page applications if you add a JavaScript app to them. I won't go into too much detail because I've personally never actually used it, but I do find it very interesting. This brings me to the HOWL stack, which basically is hypermedia on whatever you like. It was coined by Carson Gross, who's behind HTMX. He built a library that basically allows you to assign anchors on any tag, anchor links on any tag of the browser and of the web page, and not just the A or form tag. And when you receive HTML back from those links, that HTML will be merged into the page instead of completely replacing the page. This means that we can get much more seamless interactions with the with links. So, like we saw, like it's written here, normally it's only A or anchor and forms that can do HTTP requests. Not all the verbs are available, and the page has to be changed completely to show the new state. So we see that because HTMX allows you to replace just part of the page with any tag, it makes it much easier to build interactive applications. There are some limits to what you can do with HTMX. And most people will end up going for a JavaScript library that gives you like a nice DSL for building interactivity in the page for stuff that's not network related. So Alpine.js is pretty popular. It takes, I think it uses the VDOM, the virtual DOM model from Vue to check the state for any state changes and reactively update the HTML that depends on it. Then there's also, I haven't written it in here, but there's Hyperview, which is written by the gang behind HTMX, and that's, I think it's a DSL based on HyperCard, but for JavaScript and HTML. So what you do realize when you build something with HTMX is that you need the JavaScript, so for certain interactions. And if Alpine.js or Hyperview works for you, that's great. I have worked with something else called Datastar. It's a library that was written in TypeScript by a guy named Delaney. He has a background in video game development, notably The Sims. And he does a lot of work with Nats, which is, I haven't used personally, but it's sort of an event used for setting up event queues and a lot of network interactions. He's very performance oriented. So he gave a talk a week ago on the subject in the US, and if you look at his slides, it will be a lot more about the performance of Datastar than my talk, which is more about infrastructure and how to set it up on OpenBSD. So basically, Datastar, it's simply a global store of reactive signals with a DSL that allows you to access those DSL in JavaScript code easily. It's also a framework for registering plugins. Now, these plugins, they can register new signals. They can register actions, which, did I write there? Yeah. Actions, signal is $1 signal. Action is $2 action. And you can also create new attributes that will have behaviors that depends on the plugin. The attributes Datastar uses are standard compliant HTML. That means that Datastar apps are actually just HTML. And any browser can read them. So you just write data dash and the attribute you want to use. The expressions that are created in the data attributes, they're watched by Datastar, and if any of the signals that is used by it is changed, then Datastar will recompute those expressions. Datastar is also a set of standard plugins that we'll explore. You have the core of Datastar is very, very small. Datastar, with all the standard plugins, goes up to about 14 kilobytes. Then we see HTMX with Alpine, about 36 kilobytes. And like Next.js is 86 kilobytes. So it's not large. This is not necessarily large page sizes, but when you add to them a whole other app as well, they can get pretty heavy. So the attributes plugin gives you a few useful attributes, notably data-store that allows you to store new signals, create new signals. It just takes JSON and turns it into a tree, and every key becomes a signal. Then you can assign, it allows you to assign expression to any vanilla HTML attribute with data bind, and it allows you to attach expressions to event listeners with data on. There are data model also creates a bidirectional binding between an input and a signal. So if the signal changes, the input gets updated, and vice versa. I'm working on a patch right now where the bidirectional binding will be validated with the browser APIs. So it's really it's quite simple. It's only adding 2 or 3 lines, but famous last words. And so the updates won't propagate to the signal or the input if the update isn't valid according to the input. There are a few other attributes that you can find in the reference page. You'll find in general the data star has very little custom attributes. They're all, Delaney did a pretty good job of trying to find the smallest set of primitives that could express the most needs as possible. Which is one problem I find with stuff like Alpine and HTMX is that they have a lot of custom tags, and the number of tags just keeps expanding. So data star can be used to improve little websites without doing anything fancy. This presentation is a data star application. It's just HTML. It's HTML pages with some code at the top of the body to bind an event listener to the arrow keys, and that's linked to the ID of the previous or next button. And by clicking on the arrow keys, I can navigate between the slides. So it's very simple. You need to understand a little bit of JavaScript to do that kind of stuff, but it stays simple. Now, if it was only this, you wouldn't really need data star. You could do that with just a script tag, but it gets more interesting towards the end. So here we have a demo of just the input model. So let's say I write my name here. You can see that it's reactively being updated here, and if I click on it, my name appears here. The last few months, I worked on a plugin called the Inspector. It allows you to, it's just a web component you can insert into any page. And you can see all the different versions of the global store and see how they change with time. You can also see all the events that have played out with, in some cases, when those events do a diff. Those events change the HTML. You'll be able to see the diff between the two. I find that can be useful in certain types of applications. You'll see, you get also a log when you click on an event or similar stuff. Now we get to the backend plugin. Backend plugin is all about allowing DataStar to interact with a server. So this is where it gets really interesting for working with OpenBSD. So $, the name of your method, parenthesis, your URL. That will initiate an event stream with the server, which the server then receives the request, initiates the stream, and starts sending down events. These events can take many shapes. The main ones are the redirect event that allows you to move the user from one page to the other. The signal update event that allows the server to update this signal on the client. We'll see. I'll talk a little bit later about how that can be really useful with web components. And finally, the fragment event, that just, the server specifies a merging strategy and a selector and sends a fragment of HTML. Datastar receives that and says, okay, well, the selector tells me to select this element and to change it with the fragment depending on the merging strategies. That can be, it can be replace the inner HTML, replace the outer HTML. It can be append, prepend. It can be, it can be append to children or prepend to children and insert before or insert after. So this allows you to do, there's also a merge where we'll try to merge the two different states together. This allows you to do a lot of stuff, basically. And compared to HTMX, the big difference here is that it's a stream by default. And the plugin doesn't offer any other options, actually. It's really just a stream. And compared to many other streamed update things, it's not a WebSocket. It's just an event stream with server-sent events. So we're not polling the server for updates. We don't have sockets to set up. It's really just the server that decides to send an update when it feels a need to. How does this work on OpenBSD? It's really, really simple. So you need to start HTTPD and slow CGI, and you have to make sure your firewall allows you to talk to your HTTP port. Now, other things we need to keep in mind, the HTTPD daemon on OpenBSD is crooted, and that means that we need to either compile statically our applications or make sure all the dependencies are in the croot at the right place. So here you see a basic configuration. This is the configuration of the presentation. I think it's pretty simple. You listen on a specific port. You send requests for OpenBSD Datastar go to HTML, and request a CGI bin, return a CGI application. I've prepared, in my description of the presentation, I said I was going to present how to do Perl, but I didn't get the time to get to that. I got married this summer. But I do have a C example and a KSH example. Because as I might have forgotten to say at the beginning of the presentation, this is all OpenBSD base. There are no other tools written on. Actually, this server this is running on is the one from OpenBSD Amsterdam. And all I did to it was configure HTTPD, enable slow CGI, and copy the files. So we can click here. This example you'll see is completely driven by a server-sent event. So if I click on the C example, you see it's being sent over. I included the inspector for people who want to go see what events happened. This is all the code you need to do a server-sent event in CGI with C. So with the nice added bonus of pledge. So we're sure all it's doing is input-output. So we need to create an event stream, we want it to be kept alive. And after that, we want to flush a buffer. And we need a new line at the end of each line. And when we're done with like a first event, we need to add another new line. And then we flush a buffer. It's sent to the client. Client understands it's an event stream, and then we start sending events. Data star fragment. If it would be a redirect, it'd be data star dash redirect. And then we put in our selector, merge, fragment. What you see here is really is the same code as what's powering the tab. If I do it with, if I look at the KSH example, this is all it does as well. So I'm not necessarily telling you to write web apps in KSH, but for internal stuff, it can be really simple and easy. So one thing to keep in mind about SSC in general is just that it sends, since it's a stream, the client it can't really know if the stream stopped just because there's a network problem, or if there's a server problem, or if any other problem happened. So it will retry by default, unless it's capable of detecting that there's really a problem with the shape of the event that's being sent. That means that we need the ID here. That's part of the SSC HTTP standard. And the ID, it tells you what event are we at. So after the client reconnects, we can, if the interaction is idempotent, doesn't matter, you just keep going. But if there are mutations in your process, then you'll want to start back from the last event that succeeded. It's not that hard to do. You just need to do, like, for example, like a switch case on the event and start back from there. Next example. So this brings us to real-time applications. Generally, when you want to get into more complex data store applications, it's a good idea to have the page on its initial load start a connection to the server and get the, with data on load, and get the server, probably that your HTML page has been pre-rendered before, but then you want it to be updated with any changes to the state by the server. This is very lightweight, by the way. You can do, for instance, Delaney, he created a game engine in a web component that he puts on the page. When the page loads, it sends a request to the server, and the server starts pushing new frame updates to the client. And since it's just text, it's not that much the text, he actually just re-renders the whole frame every time he gets an update to his to the frame signal that he's binded to the new frame attribute on his web component. And then he managed to make a 3D web engine work very efficiently with that. So yeah, basically you have this get request that synchronizes the state, and your other requests around, they just create mutations that notify the main get thread, which will then take care of formatting the view and sending the update. So you really have only one thread that's taking care of making sure the application view is updated. Event queues are really useful for this. You'll see in the next. In this example, I just wrote a C file that uses KQ to do to track the state of a file. Whenever there's a modification to the file, we send the new state of it to the client. If anybody is on the website right now, they can actually submit messages, and it will send. Yeah, so I can say, thanks for listening. So on and so forth. What's cool about that, since we're not polling and stuff like that, if I have another process on the server that modifies that that file that we're watching, it's going to show directly on the app. I think with that we can do some pretty cool stuff. The examples I've shown here are pretty simple, but there's not really a limit to what you can do. I think all the tools to replace single-page applications are in there, and it's not really important what tool you use, be it HTMX, Alpine, Datastar. For me, the important part is that the code we're sending to our clients is not too large, and the actual and that the code that's being run on the client isn't too heavy either, because some people live in parts of the world where they don't have good internet access. They might not have good computers. I mean, even my computer's getting pretty old nowadays. It's for Generation X1 Carbon that I got refurbished. So sometimes when I'm doing weird stuff on web browsers, my computer starts lagging a lot. Now, I think that was pretty much it. Guramafagot. I'm not Irish, so my pronunciation is probably bad. My grandmother's from Limerick, apparently, though. So, any questions, you can send them to my email or come talk to me in the hall. Or ask them right now if we still have time. Yep, good. So, yeah, that's it.
Any questions? You mentioned Max before. So did the author of this framework use that as a backend or something as the event queue itself?
So the
Publisher writing events into that?
Yeah. So the question was if the author of Datastar uses Nats as a backend service, and the answer is yes. He actually published a website publicizing something called Gonads, which is Go with Nats with Datastar.
Oh, I thought you said Gonads.
Yeah.
I thought it was Gonads.
Yeah. That's the name of the.
What it is?
That's the name of the stack.
You can tell he's a game developer.
Yeah, he's funny. And he's managed to do some really, really efficient stuff with Nats and Datastar. He's streamed. He's taken examples of benchmarks in React and HTMX and transferred them to Datastar. And sometimes they break because Datastar is too quick. And the sending events on event streams is too quick for and it makes too many updates per second. Any other questions? Great.
You're ready?
Yep.
Cool.
Good to go.
So, welcome all back to Voyer number E for our OpenBSD talk. And now it's Vocala. This was actually one of my talks that I wanted to see for sure. I'm using VMD a lot. Maybe some of you know. So I'm really looking forward to see what David has been coding. So, take it away.
Thanks. So, I'll be talking a little bit about VMD, mostly kind of an update of what's happened in the last 2 years since I landed a pretty major change. The title is, 2 releases later, but it's actually, realistically speaking, closer to 4 because if you were at EuroBSDCon in Tokyo almost 2 years ago, whatever it was, you might have seen the first part of this talk where I started talking about the initial redesign I was doing. I gave an update in Ottawa, not this year, but last. And this is kind of a recap of all the things I found along the way, kind of lessons learned. So I can go a little bit deep into some areas if people have some questions later on. I'm going to try to keep it a little bit high level because I know for a fact most people are not hacking on VMD in OpenBSD. Because if you were, I would be very grateful and I'd have more help. A little bit about myself, if you didn't pick it up from the commentary about Quebec. I live just south of Canada in the state of Vermont. If you're not familiar with U.S. geography. It's about 4 hours north of New York, about 3.5 hours northwest of Boston, somewhere up there. I'm a 40-minute drive from the Canadian border, so I like to make fun of it. I'm not originally from there, I'm from the Boston area. My presentations always feature pictures of my dogs, primarily, so you'll see Maple and Moxie. Maple's 8, Moxie's now 3. They're not with me on this trip, unfortunately. And also their dog friend, Fritz. So, covered a little bit about this already, but kind of the area that I'm going to focus on is really the plumbing of VMD, like the really unsexy part, where I found a lot of things that need love and care and fixing. That by making VMD multi-process when it comes to VMs themselves. VMD itself was multi-process to begin with, but now if you run a VM under VMD, you actually get devices emulated as their independent processes. They all talk to each other through IPC, and this is the area where things are really the hardest to redesign VMD to be more modular. I'm going to talk about basically the good, the bad, and the ugly. So first, what went well, what lessons did I learn? Where did things start to come apart, and where were things kind of unexpectedly horrific in my experience? And then I'll kind of close this talk with a little bit of a kind of preview of what I'm thinking of working on next, time permitting, mostly as a way to kind of motivate me to keep doing it and put it kind of, give you guys an excuse to harass me about where those things are in the future. But first, if you never saw any of his previous talks or you haven't looked at the paper I put together for Tokyo 2 years ago, what do I mean when I'm talking about multiprocess? So this idea came to me mostly from tinkering on VMD and VMM for quite some time. Hypervisors or VMs or the infrastructure powering VMs are fantastic targets if you're looking to break things or steal things or just do things, because that's basically what the entire cloud computing world nowadays is built on. All the big cloud vendors basically have their own spin of some hypervisor, whether they wrote it from scratch, whether they derived it from something else. And they spend a lot of time hardening this infrastructure, primarily because they need to have this multi-tenant cloud to make it look like your VM is special and unique and individual, even though you might be sharing compute with somebody else. And then most importantly, they need to move that thing around. Whether you know it or not, they can actually move your workload seamlessly behind the scenes. VMD can't really do that, but they can do it. Some CVEs that are particularly of interest when talking about hypervisor escapes. So usually what people are trying to do is they can get onto the infrastructure and they usually want to break out of the virtual machine. People tend to use VMs for, I'll say sandboxing. It's a weird term in this case. And some people think, okay, it's safe, I'm putting this program in a VM, it can't do any harm. Obviously, that's a little bit naive. Some of the best ones have been, in my opinion, from about 9 to 10 years now, related to device emulation in QEMU. So the floppy disk controller, which I bet most people who spin up a VM in Linux, who, they might be using whatever GUIs wrapped around libvirt or whatever these days, they might actually boot up some emulated hardware that they don't need, including a floppy disk controller, just because. But these devices lingering can actually prevent or provide footholds for people to break out of the guest, manipulate the state of the host. So there's some cool, these are actually links once I publish the PDF to be able to cook on them. But basically the theme is the same. There's some emulated device as a guest workload in the VM. You get to talk to that device, because that's how you communicate to the outside world, typically. And if you can get that device to do dumb things, a buffer overflow or stack overflow or something, or misemulate writes to memory somewhere, you can now control behavior on the host. So the general idea from a threat perspective is, okay, it's not like you can't not provide devices, because then it's not a computer you're emulating anymore. What's the point if there's no storage or network? How many people are running a VM with zero networking? Maybe on your local machine, but it's very low value. You're not going to be able to build a business around that. People have to put stuff on the internet. So how do you really mitigate the blast rate of this stuff? OpenBSD is not immune to it either. I remember my first hackathon for OpenBSD. I showed up with a plan to do something. That plan got thrown out the window immediately because somebody had reported the ability to inject packets into a VMD instance to cause buffer overflows. Oh, cool. Now we get to tinker in this code that I didn't want to touch. So I saw, working on this stuff and being a self-described lazy individual, I want to make stuff not break as much as possible, because I don't want to have to come back and fix it, because I'm lazy, and I do this mostly as a hobby. I'm not paid to work on OpenBSD or VMD. And I came across, once upon a time, QEMU had a talk given by some Oracle engineers who split QEMU out into multiple processes. Now, I think their intention was different than doing security hardening and whatnot. It was maybe more about shared devices for performance efficiencies and things like that. Because imagine if you created a network process that tied all the VMs together for them to exchange data as if they're on a private network. Maybe there's some efficiency to gain. But you can also use it for hardening. The talk was given, there's some good patches that were posted and merged in, and I've never seen or heard of anyone ever using it. I'm assuming since they're Oracle engineers, Oracle Cloud uses it. I don't know if anyone here works at Oracle and can corroborate that. But you go to the wiki page, and it's documentation about the design, not about how you use it. And you basically have to start a separate process and link all these things together, and it just looked like hell. Which is really not how we like to build daemons in OpenBSD. Say what you want about, the bugs or fixing in the code itself, but usually from a user perspective, we like to keep it as simple as possible. So the general idea was to take the existing VMD design. So I wasn't around during the initial design delivery of it, but the architecture of VMD traditionally has been like a lot of the privilege separated daemons in OpenBSD. You've got the kind of primary parent process, in this case called VMD in this diagram. It'll do this dance of fork and exec, fork and exec, fork and exec to create a bunch of child processes. And each of these is usually specialized to do something, because then we layer on different privilege dropping techniques. So there's a control process which handles if you're using vmctl to start a VM or to connect with a console. That thing will talk to the control process. The VMM process talks to the kernel to actually start or stop a VM, to run a vCPU, for instance. Privilege process, it's kind of an appendage these days that I think all it does is a single call to do some sort of network interface address assignment or something like that. I can't even remember. AgentX is relatively self-explanatory if you know what AgentX is. But then the general idea was the VMM process would really be the one that forks and creates a VM that you'd be running. Now originally, if you started up a guest, you would get a single process and that would do everything. It would emulate the disks, the network, the CPUs, all this stuff. And for the longest time, and I still think to today, VMD is the only userland ship base program that uses pthreads. So if you think about like how odd that is, because it's not odd maybe in other BSDs, but in OpenBSD, multi-threading is usually not the design used for building any kind of base programs. So that kind of makes this little oddity to begin with. It makes it hard for contributors, makes it hard for people to debug. And it was actually the reason that I started playing with VMD and hacking on it, because it didn't work half the time for me. Because there were race conditions, because it was multi-threaded, and you could just have your Linux guest just poof, crash, gone. And apparently that was enough to trick me into working on it, and here I am today. So what I did previously, around 7.4 or so, was, okay, so that VM is one process. There's a lot of complexity in there. Taking the inspiration from the QEMU stuff, so this wasn't solely my idea. It was, okay, let's take these devices, especially the commonly used ones, so the block device and the network device. Pretty much every guest will have usually at least one, if not both of those, maybe even multiple. Split those out into their own separate processes and let them only do what they need to do. So if I'm a disk device emulating a hard disk, I just need a file descriptor that points to the file or files on disks. It might be multiple file descriptors, really. QCOW2 images can have all sorts of layers. But if it's just a raw disk image, I just need a file descriptor to read and write and access to guest memory, and then some ability to be kicked in the head when the vCPU is trying to read or write to one of my registers. So that was really all the work that I presented previously. So nowadays, the actual architecture reflects everything here. I did a weird twist and that tweaked my back. So now, like if you have two network interfaces, they actually fork an exec off the VM process. They end up using pledge and other kind of capability restricting like approaches to only do what they need to do. So now the idea is if somebody finds an exploit like they did for the DHCP emulation in VMD, and they bust out into the host process, they'll end up here, and this will have a lot more restrictions than one step up above, because the VM process needs to actually run the vCPU and do all these other things, and now we've really got to separate it out into just individual concerns. So that's all generally a nice design. And this was really my goal, summed up basically in this one slide. So, what really impact would an end user have? So a lot of people use OpenBSD and just upgrade every release, never really read the release notes, don't even necessarily know what's changed. And in general, you shouldn't, I know I'm being recorded, but I mean, you shouldn't have to read the release notes, so you should be able to upgrade. I mean, sometimes you're gonna have to go in and change something because we have to deprecate stuff from time to time, but the world shouldn't come crashing down because you did an upgrade. You shouldn't have to learn a bunch of new command line arguments. VMD was already designed to be simple. You can start a VM just by saying vmctl start, and then say, okay, I want -L as a local network interface, C is give me console access right away from that process. D is a disk, and here's my disk image. M is the amount of memory I'm going to give it, and then the VM name. Which, if you use QEMU or even some other hypervisors, like this is simple. Like it really doesn't get much simpler than this. When I landed those changes, if you can tell, if you diff these things, there's no difference. Like it's the exact same thing. So you would benefit from the redesign. Without having to learn anything new. So that went well. I think, I don't think I received any angry emails or complaints that people's like scripts or their their habits of what they type changed or broke. And then we also were able to do some better, cooler things as a result. So when all that stuff was crammed into the one VM process, it was a lot to wrap your head around. The same process doing networking and disk I/O and vCPU emulation, all this stuff, it's a pain in the ass to
get somebody interested in fixing or tweaking or enhancing. So, our initial VirtIO implementations on the device emulation side, they did the bare minimum. It got things working, and there was a lot of room for improvement, but making those changes was extremely haphazard. You had to really know the code, unfortunately, and how to sift through what you didn't care about to get to what you did to make the change. And quite frankly, it was really daunting, probably the worst in terms of, I don't know, I'd say it's probably in the top 3, probably with OpenSSH and SMTPD as being probably the scariest things for somebody to come by and touch. Although I'm sure we want people to touch other daemons more frequently as well. But by splitting everything out, it allowed even me, who had been working on the code for a long time, to then focus and say, okay, where can we make stuff better? Now I got all the network emulation stuff in one file. It's not like surrounded by all this block IO stuff and all this other emulation. And that's where a lot of performance enhancements came from. So I started down this path of maybe hardening VMD, but in reality, this ended up being a big kind of performance boost. So by splitting out like the disks in the network, I was then able to read the code better, quite frankly, and found all these inefficiencies. We were just copying data from buffer to buffer to buffer over and over again. So if you see any kind of latency improvements in the last 2 or 3 releases, it's probably entirely related to changes that came as a result. So nowadays, if you're using raw disks, we're actually doing zero copy, where the guest gives us some buffer of data to write to the file. We're no longer copying it into some intermediary buffer in VMD and then writing it out to the file. We're just going directly from the guest memory into the file itself. And then the best thing was most of these changes were net negative, actually deleting code. And I went back and I looked at my diffs I committed, and at least for the VirtIO block rewrite, I mean, it was practically a rewrite. It was actually 80 lines shorter, which is pretty substantial when you look at that file itself. And then since it was a lot more efficient, we're not copying stuff around, the host CPU utilization actually went down as well under load. So, and if you run guests that are not OpenBSD, you actually see pretty good benefit here, because Linux guests make better use generally. I mean, we can't support FreeBSD yet or NetBSD fully. I can tell you over drinks what needs to be done. But Linux does a better job of using multiple buffers with VirtIO to be able to push more data faster, basically, is the net of it. And VMD was now able to take better advantage of it. So your workload in Linux under OpenBSD actually improved probably more noticeably than OpenBSD guests under OpenBSD, which the Linux guests were actually already pretty performant. The other cool thing was the network emulation. If you ever did any heavy network stuff with VMD, so like if you had an OpenBSD Amsterdam host, and you're trying to do any sort of streaming of media or anything that you'd notice latency spikes, like tail latencies. If you weren't using maybe UDP or something like that, that device emulation was entirely single-threaded. So sending data over the network, receiving data off the network, dealing with all the inter-process communication from the VMD process or the VM process, all one single event loop, which you basically could, if you did it right, you could starve one side of the transmitter-receive networking just using iPerf3 or something, if I remember correctly. It was very simple to do. Now everything was in one file. It was a lot easier to now introduce multi-threading. If I had done that before, it would have been an absolute nightmare. I would not have signed up my personal time to add multi-threading to VirtIO networking without it being in a dedicated kind of process. So now it's a lot easier to modify this stuff. So if you're not aware, VMD actually has its own kind of built-in DHCP service. So when I did say -L on the couple slides ago, not only does it gives me an interface, but it gives me a quote local interface, and it sets up, if you send a DHCP request out on that interface from the guest, we intercept it. We're actually doing packet inspection on those packets before we put them out on the network. If it looks like it's DHCP, we intercept it, process it within the VM VirtIO network emulation, and will inject the response into the receive side. So it's actually a pretty interesting place that if you wanted to do kind of weird hacking on kind of packet intercept stuff, the pieces are a lot more accessible now. So that was all. Those are all positive, happy things. I mean, all this stuff sounds like it went well, but that's really not the case at all. The first thing was really all of the IPC plumbing here. That's Moxie when she was little, sniffing Maple's butt. I think it's appropriate for this slide. This is an area that I think could probably be simplified, but in order to have all these separate processes for emulating a VM, there are all sorts of different kind of messaging patterns that need to occur. And really, they kind of fall into two categories, synchronous and asynchronous. The most, probably easiest to understand synchronous channel need is if I'm a vCPU and I go to read a register using port IO. So we don't emulate MMIO yet with VMD. So we use port IO. We only support Intel-based devices. So I'm actually using an in or an out instruction in this case from a port. That CPU is basically going to assume it's going to get data back. It's basically a request reply pattern. Like it has to block. Like it's not able to submit a request and then be notified via an interrupt or something or poll for the result. So basically, we have to have the vCPU thread in the VM process wait for another process to receive that message saying, hey, somebody's trying to read this register. Go get that value. Reading a register might mutate state based off of what register it is. So handle that. And then, oh, you need to send the reply back because then I need to give it back to the vCPU thread. And this is a little bit of a pain in the ass, to put it bluntly, because if you've ever looked at any of the heavily privsep daemons in OpenBSD built in the last 10 years or so, I think, so HTTPD, RelayD, VMD, I'm sure there's others, they all use a combination of libevent, which is in base, libevent 1 dot whatever, can't remember what we have currently, and then a framework called iMessage to do the IPC messaging. And it's all basically designed to be asynchronous. So by doing some synchronous blocking and communication mixed in with this asynchronous event loop stuff, you get real interesting friction and some really heinous code. So that was really the biggest headache. The asynchronous stuff, really not that bad. It actually got a little bit better because now if you wanted to say pause, let's say you say vmctl pause and you want to just suspend a VM and say stop processing. We now actually broadcast the pause event out to all the child processes. So if you have like 5 network interfaces, I don't know, they'll all get a pause message and we wait for them all to respond and say I'm paused, and then we kind of quiesce the whole thing. So this is kind of a visualization of that headache and where this is the most problematic. I drew this like 2 years ago on my iPad on a plane. So I'm not an artist and my handwriting is very bad. It's actually probably not too bad here. But the general flow, so like if you want to think about how something like that simple register read gets emulated. So you'll have a driver in your guest somewhere and it says, okay, I want to go read the status register for this VirtIO device. So it does some sort of operation, some instruction, causes a VM exit. We fall out of the kernel into VMD. VMD looks at the thing and says, okay, it's trying to read this port. This port I know is associated with this VirtIO device. This VirtIO device is this process over here. Go grab the channel to that process, send an event down that way. And now I got to wait. So it kind of goes around this loop. So we get kicked out of the guest, talk to the vCPU. It might send, in this case, it might send something over the synchronous or asynchronous channels, depending on what type of operation it is. The device will do the emulation, and then either synchronously or asynchronously reply back. If it's asynchronous, usually it'll be like, okay, I've finished using all the buffers you gave me. Now I want to send an interrupt. So what happens is the device process actually sends an asynchronous message to the VM and says, hey, go kick this vCPU, go generate an interrupt for us. there's a lot of interconnects and moving pieces. So this is where it's kind of starts to get pretty ugly. To kind of make the ugliness a little better, that's Moxie as a puppy, I think, back 3 years ago, I think now. The way all of this is really possible is a little bit of a hack in OpenBSD from before I started working on it. So all of this is made possible by shared memory between processes, effectively, that and then the IPC channels. So a guest has memory. You know, in that example, it was like 8 gigs of memory. So when you start up a VM, it goes and allocates 8 gigs of addressable virtual memory. And what happens is there's a special VMM device, IOCTL, that if you have permission to, you can say, if I have a file descriptor open for the VMM device, I can say map the guest shared memory into my address space. So this is used by these processes when they split off, because they're forking and execing, and they have their own new address space, a new layout, and all this stuff. So they need to find a way to be able to read and write to the guest address space, because that's how device emulation works effectively. So we had to add not this interface into the kernel, but then had to really take advantage of it extensively. My first implementation of this was horrible. It tried to use the shared memory framework, which used files and things like that, and it just leaked things. I don't know what was wrong, but it sucked, and I had to redo it all. And that took weeks, I think, of time. So if you use snapshots during that period of time, you might have noticed like some files appearing in /temp and running out of space in /temp, because I didn't fully understand the implications of using the file-backed approach of shared memory. But now it doesn't do that. It's a lot easier, but this is still a bit of a pain. Before every device can drop all its privileges, it still has to be able to do this. So it needs to know what that layout looks like, needs to have the file descriptor open to VMM, and then be able to make this call. The bigger problem wasn't really using that interface so much as all the new stress put on the kernel. So earlier I mentioned VMD is the only thing that's multi-process in the base install. VMD is also the only thing that uses that devVMM shared memory call. So that's the only one doing it that way. So we're a special little child, that has special privileges, it seems. Maybe privileges isn't the right word because it implies a lot more than probably mean to here. But we're basically stressing the kernel and all these other subsystems in ways that other programs in the base are not, which means we being VMD users and hackers, find things that people haven't found yet, especially as things are changing in OpenBSD. So I didn't set out to read UVM or PMAP code. I just wanted to hack on VMD. But as a result of all of this stuff, I had to, because all that shared memory stuff started putting weird pressures on the virtual memory subsystem in OpenBSD. If you want to get into the history of OpenBSD and some of the code, I mean, you can go look at UVM files. It's in sys/UVM or something. A lot of it comes from around the NetBSD days before the project forked off, and you'll see code comments in there that will make you kind of shiver, because they're probably from 25 years ago of someone should come back in here and look at this, or guess what? I don't think anyone did. So. And NetBSD and OpenBSD have diverged a lot in UVM. I think FreeBSD uses a completely different virtual memory framework these days. So NetBSD is the only one that I think we share some common base with. But if you look at the two side by side, they're very, very different in the kind of ways they've grown. And there's a particular memory corruption I've been chasing now for 2 years, at least 2 years. So if anyone in this room has a dual Intel Xeon machine that is doing nothing, or you don't have any use for 30 days or so, I would love to bang on it, because it's the only architecture that will surface this particular memory corruption. We've had some folks working on pushing kernel locks around and unlocking things, and this has only gotten easier to find with multiple processes sharing address space or subsets of an address space. Because what happens is during teardown, the teardown of these address spaces, it's not supposed to be racing, but it seems to be. And I'm finding these fun things where we're corrupting pools of kernel memory, and it's not good. It only happens on Intel dual socket Xeon. It doesn't happen on AMD. I spent money to boot up a dual socket AMD server in some cloud somewhere, like bare metal, to bang on it for 30 days and did not break. Can't do it on my laptop. So these are still some of the ghosts that I'm chasing that have actually kind of been more prevalent since this kind of redesign in the last 2 years. And more than once, I've been convinced that I've solved it, which makes it even more painful when it surfaces again. As of right now, I'm not of that mindset. I know it's not solved, but you asked me like a couple months ago, I was like, oh yeah, definitely, I got that. It's fixed now. It could be related to this one area that if you get a couple Guinness in me, I'll probably go on about. Intel is special. And if you ever have to do low-level stuff and look at like AMD versus Intel programmer manuals and that stuff, you'll realize that there's a very different mindset at Intel than AMD in terms of design for us, the end users of the hardware who are writing software. Part of it is their virtualization extensions are older than AMD's. I think part of it is also they kind of design fundamentally differently. Everything you do on an Intel machine to accelerate virtualization sucks. It's inefficient by design, and it creates more overhead for operating system developers and maintainers than AMD by far. And this is an area where, like, if you like pain, you can go look at. You don't even need to write the code. If you just go to either OpenBSD or NetBSD or FreeBSD, I think the NetBSD code is actually pretty good. Example to look through. The type of handling that you have to do with Intel versus AMD is just insane. So the big thing, not to go into all the details, but effectively every process usually has its own address space. An address space is usually described by some sort of page table mechanism. That's a design now that's across multiple architectures. So it's not unique to Intel or AMD-based stuff. What's unique to Intel is when they decided to do nested page table virtualization or acceleration or whatever they want to call it. Sometimes it's called two-dimensional paging, I think, although it's not frequently used. Nowadays, people just call it nested paging, I believe. I think that's usually what they call it. But basically, Intel decided we're going to take the specification for Intel page tables. We're going to make slight changes to the ones specific to virtualization, such that if you ever load a Intel, it's called an EPT, extended page table, I think is what it stands for. If you ever accidentally load that onto the CPU like a regular page table, the bits aren't going to line up right and something's going to break. AMD did the opposite. They said, okay, here's the design for virtualization. Here's the design that's been around for ages now for actual regular hardware. Let's just make sure they line up okay and you don't explode if you accidentally load it onto the CPU. And that right there is the cause of so much suffering in my current life. I've got a lot of diffs floating around that aren't going to make the next release in the next month or so. But if you're on the list, you'll probably see some stuff going on about new IPIs to do flushing of caches and other things that I need to do. Because in Intel land, you have to do everything again, is basically. It's like, oh, you built an operating system for hardware? That's great. You want to do virtualization on top? Now you got to add an extra layer of your operating system to deal with that. So if you work for Intel in this room, please don't identify yourself. So I mean, the real takeaway here is that as much as there's been pain and suffering and we've kind of surfaced a lot of bugs, from the end user perspective, if you just run VMs on your laptop using OpenBSD or you're running them on a server somewhere, the impact has been extremely minimal, if not non-existent. I mean, what you see really is different system utilization. So I'm running just a local VMD instance with a OpenBSD guest and a Debian 12 guest, just to kind of illustrate how things shake out from a process and thread perspective. So nowadays, you'll see if I I remember the commands here. If I don't display threads, this is just filtering down to just VMD or processes with VMD in the name. So you'll see things like, VMD Puffy here is the OpenBSD guest process. But you'll see Puffy/VIO block 0, which is a separate process that's emulating the block device. So anytime I do disk I/O, that's the program that's actually doing the emulation, working with the file on disk. I could shoot that thing in the head, and yeah, this whole thing might come crashing down. But the nice thing is now with VirtIO, technically, we've had a bug recently. I can't remember. Moritz isn't here. There's a particular networking scenario somebody encountered, one of the developers, and he's like, my network interface stopped working. And previously in VMD, I'm sure it would have broken the entire VM. Now it just kind of screws up a single emulated device, which is a lot easier to reset now that there's hooks to do that. And if you look at the threads, you'll now see that not only is it multiprocess, but now there's a bunch more threads. So really taking advantage of multi-core machines and emulating, some trivial hardware. OpenBSD is all single processor, so maybe this is overkill. But I've got a 12-core, 16-core machine here. Why the hell not use all 16 to run my 2 guests? So you'll see the multiple network processes here, or threads rather. The names, there we go. I can never get these right. But now you can see there's one particular thread that's related for transmission. So it's the one that will take the data off the vert queues from the guest and put them out on the wire. RX is the one that's listening to the tap device to take packets into the guest, and then there's going to be another one there that's like the main event loop. And you can see the vCPUs as well. So it looks a little bit more complex from like a system administrator point of view of monitoring the machine. But from a code and design perspective, it's a lot, I would say, cleaner, a lot simpler. It's made my life easier, which in all reality, that's what matters, right? So looking forward, if you see me talk again in the future, what might I be talking about? I mean, this has consumed the last 2-ish years of my life. It's been the primary focus of what I've done other than a lot of housekeeping and cleanup of the code. I don't think there's any other major changes I've done other than what I've just showcased. We are looking, or I am always looking for more hands or help. I just covered the microphone. I'm sure that sounded great. It's really only a couple of us that hack on VMD, none of us full-time. Not that I'm looking for anyone full-time to do it, but if this gets you interested, definitely come talk to me. I mean, this is sort of the to-do list. This is the number one bullet point is always what people ask about, when can we get multiprocessor support or SMP? It's coming in baby steps. It's just, I'll be very brutally honest for once, it's just not that exciting to me. It's exciting to have that capability. Building it is not the exciting thing. To me, I like more of the, the weird plumbing stuff. So convincing me to dedicate what time I do have to it is going to take a little bit of bribery, maybe. I don't know. ARM64 is probably more likely because myself and another developer, at least, that would be working on this do have hardware now that supports doing this. We have done the initial kind of machine-dependent, independent refactoring of VMM and VMD. You may or may not have seen a bunch of commits that occurred that all they did is shuffle files and code around. That's all it is. You can technically compile and run VMD on ARM. It does nothing. It just exits, but you can compile it. So that's step one. A couple of years, maybe we'll get there. Where my head is at right now is this thing that doesn't exist yet. I'm calling it IPC Gen. Because all of the pain I always suffer from hunting bugs in VMD is always related to that horrible plumbing diagram I showed. And that's just the device emulation part. There's also channels between all of those other processes. And if you look at like the flow control for doing something as simple as starting a VM, you run vmctl. So that's one program that talks to the control program through the Unix socket. That sends a start VM request with a bunch of parameters. That then forwards it to the VMD process. And then let me see if I can do this from memory. That will then, I believe, check permissions to see if that VM not only can be run by that user, but if it exists already, and basically look for conflicts in the global state. It will then forward that message on to the VMM process to say, I'm starting a new VM. It needs to check its own little state. And then it's going to start sending off the same message to other processes, to open file descriptors, to possibly other files and all these things. These are all individual messages that get sent while your little client is waiting for the response back. I don't even know if we wait, to be honest. I think you just get told if it failed right away or not, not if the guest actually started. So all these messages have to ping pong around, and keeping that mental model in your head if you weren't in the code is almost impossible. And so my idea is that all of this is very descriptive. It's a graph. I used to work for a graph database company. Everything's a damn graph in my mind now. I drank too much of the Kool-Aid. All of that communication can be defined in its own little language, basically. All the plumbing underneath is always the same. There's so much boilerplate in VMD, so much boilerplate. It's all like this event response type thing. Okay, I'm this process. I get this event. I do this. I send this response on success. I send this response on error. The plumbing shouldn't matter. The plumbing's there. We always generate the same event loop format. We always do the same iMessage, reading and writing, buffer filling, emptying dance. There's nothing fun or sexy there in terms of uniqueness. So why not describe the plumbing in something more dedicated? Every daemon has this problem. HTTPD, RelayD, there's common denominators here for those that know it. There's a lot of copy pasta. So pushing this behind a code generator, making it so, okay, now somebody's working on an event handler versus changing the plumbing. Or if you do change the plumbing, now you are generating the boilerplate, that type of thing. This might help future daemons, and who knows? Maybe someone will decide to write an IMAPD with this and make my life better. You never know. So I did want to close. I know we only got a couple minutes, but there's another good talk about VMD tomorrow, about some of the new stuff going in lately related to secure computing on AMD platforms. So if you use AMD and not Intel hardware, and you use VMD, you might want to check it out, because I think most modern AMD hardware would benefit from this. So I think it's same room, 4 o'clock tomorrow. But with that, I close with one other picture of my dogs. First here.
Does your work allow for direct disk access?
No. So the question is around direct disk access. I'm assuming you mean pass through like a raw device to the guest. Technically it does. However, it's not possible in OpenBSD because we do not allow passing file descriptors to raw devices. All of this is based on passing file descriptors through sockets. And the kernel explicitly forbids that type of file being passed. It's like a couple line change that could occur, but there's a lot of debate that would need to occur around supporting passing descriptors to raw devices. I tested it. It worked. I did a full install with a USB device plugged into my laptop where I used the raw USB device and it worked. But it requires a kernel hack.
It seems suboptimal that we have buffer cache in VM and in the...
Yeah, so it used to be, I don't know if it still is in Linux world, but like 15 years ago, I think the general advice was to like tell the OS, like in the guest, like don't buffer IO because it's being buffered by the host. So I don't know, maybe that's the simplest answer. I don't think there's much of a performance gain in the short term without maybe something like that. There's another question?
Yes. Now that we have Berkeley GPU in the base as a driver, I don't think we have a device in the
Right.
Wouldn't it be great?
So the question is around, would it be great to have VirtIO GPU device emulation? I think the answer is generally yes. I haven't had a need for it, so I haven't written it, but the only gotcha is I don't think our bootloader or I think CBIOS, which we use, might support it. I don't think our bootloader does necessarily. So you might not get, an actual display of the bootloader. But if somebody wanted to write a new device to emulate, that's probably the most likely one, is something to do, Visual Console. The VirtIO GPU spec is not very complicated. VirtIO itself is not too complicated when you read the spec enough. I just personally don't know anything about graphics. Graphics and networking are areas I really am ignorant of. I like to keep it that way. So if someone else wants to do it, I'm more than happy to review it. Yep. That's sort of it exists as a thought experiment, and I've kind of written drafts of what I think the language would look like for VMD. And my plan is, before I write any code, would be to extend that thought experiment to the others to see, okay, if we were to rewrite HTTPD or RelayD, what would this look like, and would it simplify things? Because if it doesn't, then I don't know if it'll be worth my time to create tooling just specifically for VMD. But who knows? Yeah, I think the areas that I want it to solve are visualizing the communication flow in a way that's concise, so anyone can just read it and understand where the messages go, and then encapsulate the file descriptor passing, because that is one of the more opaque things to understand about. Because, for instance, there's a way you can actually provide an override boot kernel image using vmctl. Now, the vmctl process will open that file and then pass the file descriptor. Now that file descriptor needs to get passed around all these little hops. So knowing where it is and where it's going and what it represents, that's one of the reasons why there's so many messages that get fired off during the start VM, because by design in the Unix world, you are only going to pass one file descriptor at a time, right? You're never going to need to pass a dozen for a QCOW base image set. So like, iMessage does one file descriptor per message max, and you just get all this ping pong going on. So there's actually a lot of errors that silently will occur in VMD that you'll never get a message for, because there's just too much communication for us to do full request reply. There's a lot of optimistic assumption that if we get this far in this communication, we're not failing. So that's why you get these obscure messages from vmctl, because it has no idea what happened. So that's where I'm kind of thinking. I'll publish my consulting rate on. So, not that I'm aware of. NetBSD, FreeBSD, and Linux all do the legwork to properly handle EPT, PMAPs, and flushing and all that stuff. It's just error prone. So like you can put that in the same category as memory mapped IO emulation as being error prone. I mean, there was just a FreeBSD CVE in the last month or so about MMIO emulation having a bug that allow a guest to write anywhere in host memory or something, or the host process memory, virtual memory. And so that's like one of the fears of where do I put my time on something that's going to create a bunch of foot guns and things I have to maintain. Like, I want to do the least risky thing that I can enjoy doing and not necessarily walk away from, but I don't want to create a bunch of bear traps to other people step in. That's why we don't have SMP yet. Thank you. Oh, cool. Sweet.
Yeah, something different.
Nice. Yeah.
Let me get that. Muted, hopefully.
Yeah, before I walk into the restroom.
So Dave, I wanted to be the first one to congratulate you as the new HTTPD. We have some other previous demons in game.
Good morning.
All right. Whatever.
Right. Welcome again to EuroBSDCon. Our next speaker is Andrew here, who will talk about his ventures with firmware updating. Good. Waiting.
All right. Hi, everybody. My name is Andrew Hughes-Fresh, A-Fresh1 at OpenBSD and pretty much everywhere on the internet. And I'm going to talk a little bit about why I ended up rewriting firmware update, but I'm going to hopefully use it as a way to explain how I see the OpenBSD's way of providing user experience and how they prioritize users and how things work. So to kind of start off, the problem that we were trying to solve is that during the OpenBSD installation process, the installer asks, do you want to start X Windows when you reboot the computer? And if you're on the laptop or whatever, you say, yes, yes, I do. And then you restart your laptop, and X doesn't start. And as a new user, that's really confusing. And as a more experienced user, it's just annoying. Now, I didn't run into this a whole lot. My laptop here is 2013 T440S. The one that I usually use at home is a 2011 X220. I don't reinstall X very often. But I do care about user experience. And the reason I heard about this a lot was that Theo would often test out new laptops and pretty regularly try OpenBSD on new hardware. And this was an extra step that he would often be like, this still is a problem. How do we want that? And so I thought, well, how hard could it be, right? It's just one reboot. How hard could it be? It's probably just a couple of lines, right? Well, back to kind of why this is the experience at all is that back in the day, manufacturers would put the firmware for their device on a flash chip on the device. And that was great, because you buy a thing off of eBay, it shows up, it just works. You don't have to worry about going and trying to find some software that maybe is behind a paywall or who knows what. But over time, firmware kept getting bigger and bigger, and manufacturers eventually realized that they didn't have to pay for storage. They could make you pay for storage and put the firmware on your hard disk and make the operating system load that firmware onto the device at runtime. And this is somewhat painful, but it's also kind of nice because it used to be that, oh, sometimes you had to boot into Windows to be able to flash a newer version of firmware or find a floppy disk or a CD-ROM drive so that you could burn an image or boot off of that to do the flashing. So there are some benefits and some downsides. But what's causing this problem is that now that the firmware is separate from the device, they can put a distribution license on that firmware. And that means people have to think about that license. And now that that's the case, some people really, really care about that. I gave this talk at FOSSI, the Free Open Source Software Yearly Conference in Portland, Oregon, a little while ago. And last year, they ran a special 802.11b network because there is a free software, open source firmware for those devices so that they can run their whole system as open source. This last year, they had some problems getting it set up with the venue and stuff, but they want it, they were trying to, and they care. OpenBSD doesn't care quite to that level as far as this goes. And manufacturers have even different priorities as to what they care about as far as licensing on firmware goes. OpenBSD cares really a lot about licenses. And like, they have their own Wi-Fi stack that is not the same as everybody else's. And they do use the same DRM, Direct Rendering Manager, graphics stack as Linux does and as most everybody else does, because it has an acceptable license and provides that functionality that's necessary. But I really got several emails from folks patiently explaining to me that Perl doesn't use only the GPL, and so it didn't belong in the source GNU directory. And so I was really glad when we redefined what GNU stood for in OpenBSD. And we have some unacceptable things in that, in the base system, mostly in this directory here. But even in the source GNU directory, there are limits to what unacceptable things can be imported, and those limits keep getting kind of tightened down as time goes on. There's never been a time when CDDL license things could go into base, GPL3 things could go into base, Apache 2 licenses, things like that. But now, at this point, there's not even any sort of GPL license that is really acceptable for going to the base system. Although updates to existing software that's in there, if the license remains the same, are acceptable in most cases. Some things that are in here, other than Perl, are the GNU CVS. There is an open CVS in the base system, but it's not fully functional quite yet. Nobody seems to be super interested in fixing it. Clang LLVM is in there now, which also is not a GNU license, as well as several things that are, like some different versions of GCC that have GPL2 license and work on architectures that Clang doesn't support. But what makes an acceptable license for firmware? And OpenBSD's kind of perspective on this is, well, that firmware isn't running inside of the operating system. It's running on its own device. And so if that firmware was on a flash chip on the device, would we care what its license was? And kind of decided that it's fine. We don't really care whether it's open source, what the license is. But what we care about, now that we have to possibly distribute that code with OpenBSD, we need to make sure that the distribution license on that firmware, or possibly just a firmware blob, doesn't add any additional limitations to OpenBSD itself and how OpenBSD can be distributed. And there are lots of firmwares that are part of the base system that that have a license that allows for this. But there are also a lot of firmwares that have a license that is too restrictive to be included with OpenBSD itself. And a subset of those licenses, subset of those firmware that have that more restrictive license, do allow distribution. And that's some of the most important ones that we're going to talk about. These are mostly Wi-Fi adapters and video graphics cards, but also like motherboard chipsets and stuff like that have a license that is not open enough to be included in the base system. That doesn't necessarily mean that's always going to be the case. If any of you are working for Intel, don't let Dave know, but if you can talk to somebody and get the firmware license adjusted so that we can add it to the base system, that'd be great. Kevlo talked to somebody at Realtek and was able to talk to the right person and explain to them that whatever this patent clause that they had in there was not acceptable. It was added additional restrictions and made it so that people who wanted to use Realtek hardware maybe would choose not to, and explained it in a way that made Realtek understand the problem, and they changed their license, and now the Realtek software, or Realtek firmware, is now a part of the base system. And we actually had to write code in firmware update to handle that situation where the code moved from being outside to inside in the base system. But it was really just this one driver. So like I said, if you know somebody who can get those licenses changed, then we can test out the code that does this a little more and work out more of the bugs that are, I'm sure, lurking in there that haven't had a whole lot of use. Anyway, so we have this hardware that has firmware that doesn't come with the base system, but we still want OpenBSD to run on it, and more modern hardware has firmware that's like this. But we still need to allow people to, or people still need to be able to use OpenBSD for whatever purpose that they need it for. Maybe those people don't get to use some of those devices that they can't agree to the licenses for those firmware. For example, that Realtek firmware, I think, said something along the lines of, if you use our firmware, you can't sue us for infringing on your patents or something silly like this. Well, I don't have any patents personally, so I'm perfectly happy to agree to that limitation to use a Realtek card if I needed one. But a lot of people maybe couldn't. But the rest of us that are able to agree to that don't have to suffer. And so, like I said, OpenBSD really isn't going to say, well, I really want to use this Intel graphics card, even if it has, that's in my laptop, even if it has bad license on the firmware, so I'll just do it anyway. They just say, no, I'm sorry, it doesn't work, so you can't use that hardware. And it just isn't supported, and that leads to suffering, and nobody on OpenBSD likes suffering. So I swear that this was the case. I don't remember which one, but there used to be a device where the man page said, okay, you go to this web page, and you follow this link, and you download this firmware, and then you extract it, and you copy it into this directory, and then your hardware might work, as long as everything went right. And that was terrible. But it had a chance of working hardware. But somebody figured out that we could move, with the license on a lot of these firmware, we could move the firmware into the ports and packages system and have it outside of the base system, but make it easily installable. And so there was a bunch of time put into adding a firmware with different licenses to that, to the ports and packages tree. And that made it a lot easier to install. You didn't have to go to some random web page, but you did have to go look in the D message and figure out, do I have a piece of hardware that needs firmware? Does it say that in there somewhere? What's the driver name? How do I map that driver name to the name of the firmware? And then how do I install that? All of this. And it was not terribly difficult, but it wasn't easy. So Halix said, oh, well, that's really kind of easy to automate. And so pretty soon he wrote a little wrapper shell script that would go look in the D message for you. It recognized which devices needed firmware and knew how to translate that to the correct name and would install them and call the package tools to install the package for you. And that initial firmware update tool was run during the RC.first time. OpenBSD, of course, uses shell-based RC system still. And what happens during startups, it looks for this RC.first time script, and if it sees it, it runs that script, and then it deletes it. So the installer would use that system to tell OpenBSD on the first run to run firmware update, scan the D message, and install whatever firmware packages were necessary. And that's worked great, except of course that happened during that first boot, after the kernel had already started, and it was too late to load the firmware for wireless cards or video drivers or stuff like that, so X Windows wouldn't start. And that, of course, is the entire problem we're trying to solve. So the OpenBSD package are written in Perl, and that's a lot because Perl is really good at dealing with the messes that humans make. Things like version numbers and dependencies and stuff like that. I think it's entirely possible that Tom over here will rewrite the package system in PHP and get PHP imported into base. It could happen, or somebody else could write it in a different language. I don't think it's probably very likely. But in any case, Mark Espy rewrote that shell script-based firmware update tool and embedded it more deeply into the package system and rewrote it in Perl. And by doing that, he was able to add some features. Specifically that, one of them specifically was that it could register the firmware as being firmware and say, this is firmware, so if you're running as the normal package tools, ignore it and don't try and do anything with it. Just make them run firmware update. And back in 2015, when this happened, it was relatively common as part of the OpenBSD upgrade process for people to export a list of all of their manually installed packages and save that, then delete all of the packages that they have installed, do the upgrade, and then reinstall the packages from that list that they'd saved. I'm not sure if that was ever actually useful, and it's definitely not anymore. But it was a problem that people would have because they would say, delete all of my packages. It would delete their firmware, and now they don't have a wireless anymore once they reboot to do the upgrade. And so we were able, with this change, it would refuse to automatically delete those packages, the firmware packages, and kind of save people from shooting themselves in the foot, especially because they probably didn't necessarily realize, if they were doing this, that they had even installed those packages because they do automatically get installed on first boot in most cases. So, as you see, things continually get nicer and more polished over time as OpenBSD, as people see things that are kind of sharp corners and things like that. Kind of one of OpenBSD's mantras is always polishing the turd and making it a little bit better, a little bit shinier. So how do we solve this problem that we're dealing with? Since we're not allowed to include the firmware as part of the base system, and we really need it available before the kernel starts the first time, the only place that we really have control is there in the installer after we've gotten to the end of the install. So the OpenBSD installer is kind of a bit of a live system, but really it's just enough pieces to be able to do the install. But it does include everything necessary to do an install, so a motivated individual can use that base system or that installer image as a recovery image to recover from a lot of things which are a Bork system that's not going to boot or something like that. Usually that means I edited fstab wrong and have to go in and edit fstab to make it boot again. But Ed's your friend. But one thing that means that the installer is so limited is that Perl doesn't fit on a floppy disk even by itself. And especially not with all of the other things that are already on there. And we can't trust that the installer kernel has everything compiled into it that we need to be able to run Perl. That may work sometimes, but it's not a guarantee, and it's not something that we want to rely on. And so we weren't able to use the existing firmware update written in Perl to be able to do this. And choosing not to add complexity where it isn't needed, and thinking about why we have limitations and what those limitations bring us is one of the reasons I think that the OpenBSD has one of the best installers of NEOS. Because if you're not careful, you could end up with an installer that maybe doesn't work over a serial console or maybe it takes more than 10 minutes and a couple of dozen default answers to install the system. And this is where my side trip kind of goes off the rails a little bit, because this is one of my favorite things about OpenBSD, is that everybody kind of thinks about whether the benefits of a feature outweigh the complexity that it adds, either to the system itself or to an administrator doing overhead. A recent commit by Ingo Schwarzy implies this attitude of simplicity. You're not supposed to commit infinite numbers of items, but correctness is a virtue. OpenBSD is not here to be everything for everyone. Instead, it tries to stay as simple as possible while meeting the needs of the developers and the project. Moving complexity to places where it can be handled by the people who understand it improves the user experience a lot. But sometimes that means removing features that people maybe would want. We used to have a Bluetooth stack similarly to the Wi-Fi stack, but it was getting old and nobody was adding support for newer devices and newer Bluetooth protocols and stuff. And over time, it was just getting old and kind of useless. And so nobody was stepping up kind of to add all of these new features. And so instead of having something that was complex and useless in the base system, it got deleted, thrown out. So while that may sound like less useful, it's really just not promising something that doesn't gonna work anyway. Similarly, we used to have the Apache HTTPD in base, and it was Apache 1.0 with the Apache 1 license. And then Apache 2 came out with the Apache 2 license, which we couldn't import. And so over time, fewer and fewer people were using Apache 1 and looking at it and fixing bugs and keeping this code maintained. And it was really getting kind of old and crufty. And so when Nginx came out, people were like, oh, this has a really good license. And it's really popular. People are really looking at the code a lot and improving it. We'll replace Apache with Nginx. And I think, thanks to Brynet for reminding me about the Nginx step in the middle here. I completely forgot in the beginning. But anyway, Nginx came in, I think it was in for maybe 3 releases, because even though it had a good license, every time there was an update, it was piles and piles of code that kept getting, that would get added for each update that was pulled into OpenBSD. And it was like, what is all this code doing? It worked fine already, or it had all of the features that we needed already. What is all this extra code doing? And all of that added complexity wasn't adding benefit, wasn't worth it for the features that OpenBSD needed. Because OpenBSD, one of the goals is to be fully self-hosting, which means that you have to have a way to get the source control out of CVS. You need to have a way to edit the source control with VI or MG. You need to be able to compile it with Clang or GCC. You need to be able to distribute that system that you've built over the internet, and that could be anything from firewalling and networking and BGP and whatever to an FTP daemon and a HTTP daemon. And so to be able to distribute the code out to there. And so somebody was able to convince Reich to write HTTPD, and that became the much simpler version of an HTTP daemon, and we were able to get rid of Nginx for something much, much simpler, but only had the features that were really necessary. Similarly, along that line, sudo was an OpenBSD, OpenBSD was upstream for sudo for quite a long time, but it had the same sort of thing. It was the one solution, similar to Nginx for web serving, the one solution for everybody. And every tiny little special need that somebody had, somebody would write a patch and say, oh, I need to add this feature to sudo. And maybe it wouldn't make it in to the actual main system, main code base itself, but a lot of times it would, and it was just becoming slowly over time more and more complicated and more feature rich for things with features that OpenBSD didn't need. So Teju then wrote doas to provide just the features that were needed by OpenBSD, and sudo is no longer in the base system, although you can install it from packages along with Nginx or Apache if you need those things. But reducing that complexity, looking at a sudo config file versus a doas config file, I can write a doas config file from memory, which I don't think I could possibly do for sudo. Another good example of this sort of prioritization of user experience is that KN recently added full disk encryption support to the installer. We've been able to use full disk encryption on OpenBSD for a long time, but it was kind of hard to set up. You had to do a bunch of manual steps. KN figured out how to add it to the installer and first added passphrase-based encryption, or passphrase-based full disk encryption, and then they added key disk-based encryption. Key disk-based still requires a little bit of manual preparation. But the amount of time spent discussing what the questions were going to be in the installer and how they were going to be phrased and how they were going to, where they were going to fit in and how they were going to work was a much significantly longer discussion to make sure that that piece of user experience was right than the actual code review or anything like that. So we'll get back on track now. Fortunately, the OpenBSD packaging format for OpenBSD packages is pretty simple. And that, if you recall, is what was used by, is now used by the firmware packages for those firmware that we're trying to install. It's very, very nearly just tarballs. Unfortunately, it's not quite as simple as just downloading and extracting a tarball, because that's a couple of lines of shell script right there, and not too bad. And as you may have inferred, up until this point, that Perl-written package manager tools were the only tools, or the only client for the OpenBSD package, ports and packages system, well, packages system anyway. And that was the only thing that like registered stuff into the package database and things like that. I guess at least on the installer, we don't have to deal with multiple people writing to that database at the same time, so that makes things a little easier. In any case, there are some things that haven't yet been removed from OpenBSD. And some of those things that haven't been removed are actually part of the install media, and those give us some really impressive capabilities. Like I said, that OpenBSD installer is written with tools that fit on a floppy disk, and it works really well. And these give us enough features that we're actually able to implement a very, very simple package system client. Fortunately, able to declare two things as part of that. The first was that there's going to be no dependency handling. No firmware could depend on another firmware or depend on something else being installed before it could work. And no parsing of version numbers. All we do is we say, you have this version installed, this version is available, or we're going to install the one that's available if they're different. So if you're testing out a new firmware, well, we're going to downgrade you because we don't care. And that's just the way we were able to make it simple enough. And with that, those two kind of really small allowances we didn't need 99+% of the complexity of a package manager. Pro tip, never ever write one. They're really, really, really complicated, and when you get to, you'll never get to the end. So because that firmware update is now, so now we've rewritten that firmware update as a shell script, a KSH shell script, and that means it's just a plain text file. And that means we don't actually have to include it as part on the install media. We can just put it into the base sets. And that means after we've installed the system, we can run that script using the KSH and the tools that are part of the installer to install this firmware that we need. And that means we don't really have to worry quite as much about the saving space as we would have to as if we were writing it in the same similar terse style that the installer's written in. And we could use a little bit of a nicer style, which was really beneficial to me. There was one other piece that we needed to be able to support this in the kernel, or in the installer, because the installer kernel has to fit on this floppy disk. And so a lot of things like graphics drivers and stuff, or video card drivers, are not compiled into the kernel. And because of that, the drivers don't attach to the devices. And so Arnagi and Theo were able to figure out how to use PCI devs or data headers and the different dev list headers to generate a list of patterns that that would be in the D message, and how to map those patterns back to the driver that they are going to attach to, even though they're not currently recognized by the kernel. And with that, we're able to so we're able to match those devices still in the current while we don't have a full kernel available. And like I said, that's written in the firmware update is written in OpenBSD KSH, and those firmware patterns are actually FN match globs, so that we can match them directly in KSH without execing an external program to make firmware update faster. My initial implementation, I think exec out to sed or something to do the matching, and it was rather slow. And because of that, and so I was testing on old alpha 166 megahertz with 128 megs of RAM that Michael Dexter got from me. And it would take several minutes to detect hardware, or to detect for hardware that needed firmware that this machine didn't even support. But by doing some of this optimization and switching the matching to be internal, I was able to get it down from several minutes down to several seconds on that machine. And on most modern machines, it's pretty much instantaneous. I mean, it is a shell script, so it's really kind of painful to pass around arbitrary strings. And there's no networking built in, but should a shell really be able to do that? I'm sure that networking, a shell with networking in it, is just a ghost story, right? Instead, we use FTP, which says it's FTP, but it's actually a TLS, FTPS, and SFTP, and HTTP, and HTTPS client, at least for HTTP GET. And unfortunately, though, it is a rather old code base. It is pledged and unveiled, which you can go read about more on the OpenBSD website or watch videos on YouTube about. But it is an older code base, and it talks to the network, and so it's kind of untrusted a little bit. So what we do when we're downloading files using it is we drop privileges. And we do that using either SU or doas. And we have to use both because SU is too big to fit on the install media, but doas, and on the install media, doas is compiled as a stripped down version that doesn't have a support a config file, it has a hard-coded config built into it. And so on the install media, we use doas to drop privileges. But when we get to the full system, because it has a config file, it's not configured to do anything, and so it doesn't work doas doesn't work at the beginning. And even if we added a config for it that said, oh, you can make firmware update work, somebody could go in and modify that and make it stop working. So instead, we have SU available, so we use SU to drop privileges when we're in a full system. And then what we can do is verify the signature on that and verify the checksums on that. And the way that works in OpenBSD is that you can get this signify key, the public key, and with that you can use signify to verify the signature of the checksum file for the base sets, and that includes the checksum of the install media or installer. So you can verify that the installer that you've downloaded was signed by somebody trusted by the OpenBSD project to do that. Inside of that installer is this public key again, which you can also get from the OpenBSD website or the OpenBSD CVS tree or the GitHub mirror or something like that, or the email that gets sent out announcing the new release has it in it. So you can compare this key and verify that it is the correct one. So then we can use that checksum. The installer has that checksum or this signature in it, so we can verify that the sets that it downloads are valid and have been signed by somebody that, that the project trusts. And that means that also in those base sets are some additional public keys. Keys for, in the OpenBSD 7.5 sets, the OpenBSD 7.6 keys are in there, so that when you go to upgrade, you already have a trusted public key available to verify the sets for OpenBSD 7.6. And it also has firmware for packages, or has a public key for packages, and also for the different firmware that we use. So what we can, in the firmware update, we can download the firmware, download the checksum file, verify its signature, download the firmware that we need, verify that it's the same firmware that was signed by somebody trusted by the system. And once we've validated that we can trust it, we can extract it and register with the package database. And to register with the package database, we use Tom's friend, Ed, to do that. And primarily this was only used for system recovery before, but the package database is actually a text-based database. And so we could use Ed we could script Ed to be able to go and modify the database and register the firmware as being installed. And I know I said we replaced Perl, but when we're running multi-user in the full system, because of that registration process, we need to lock the database to make sure that no two processes are modifying it at the same time. And so we actually use the same Perl tools to verify the package data, to lock the database to make sure that that doesn't happen. And with all that, we are able to run firmware update during install. And we actually run it quite a bit. We run it during the install or an upgrade process at the end. If you're using sysupgrade, which I highly recommend, we run it before rebooting. And at that point, we install the firmware for the destination system. So if you're upgrading from OpenBSD 7.5 to OpenBSD 7.6 in the next month or so, sysupgrade is going to install the firmware for OpenBSD 7.6 so that because the upgrade kernel that it's going to use is 4.7.6, and so we'll possibly want to use the Wi-Fi drivers, for example, or Wi-Fi firmware to bring up the network to be able to install any other firmwares that it needs and anything else that it needs network for. And then, of course, we continue to run it as part of our c.first time after the install and after we've rebooted, just in case there was something that we failed to detect or something went wrong with the networking or something like that. And with all of that, nearly 850 lines of KSH and 600 and something lines generated patterns, you no longer have to reboot after you've installed for X Windows to start. It's been doing that for a couple of years now since OpenBSD 7.1. The FAQ does have a section on adding firmware to the install image, just in case you need to install using a Wi-Fi card that the driver's on the install media, but the firmware isn't. It's kind of handy. And with that, I want to say thanks. And actually, I want to mention that if you do come to Portland, Oregon, hit me up. We do a pizza meetup every month. Hang out, talk about BSD stuff and whatever. Michael Dexter, who's here at the conference, organizes our local plug meeting. And they do talks and stuff more structured regularly and stuff. And both of those are on Calligator. And if you're there, come see us and say hi. And with that, I can, I think, take some questions.
So with the rewrite, the effect of the -A option changed.
Okay.
Previously, it would install all available firmware.
Okay.
Now it installs all available firmware relevant for your machine.
Okay.
What I used the -A for in the past was to install all available firmware for all USB devices that I have laying around, but not plugged in my machine at that time. That meant that, yeah, you just install firmware, everything's there. Whenever you plug something in, it will work. Is that a use case that will come back, or any ideas about that?
I think that would be a relatively straightforward patch. The question was, previously, firmware update -A installed all available firmware. And now it, I guess, is pretty much a no-op because it just installs the firmware that you need. Primarily, I use -A with -D to delete everything. So I guess that's not something I really considered, but I would definitely think that's a perfectly reasonable thing for it to do. It's a shell script, so I recommend looking at sending me a patch. But I could add it to my to-do list, but as with all to-do lists, it's really long. So,
I can have a look, but
yeah, it seems totally reasonable.
Well, otherwise the man page is wrong because it says that they will install all the drivers if you give it -.
And I probably...
Actually, the way is needed.
So...
I'll have a look. Thanks.
All right. Uh-oh, Tom.
Quick question. Serious question, like the PHP request case. When you said you were using Duaz, but there's a stripped down version of other binaries, is it like you compile it with a different switch, or do you actually, is it a separate actual file where you just...
No, it's... There's a define somewhere, I can't remember what it is, that says that we're compiling the kernel, install kernel, and that there's if-defs in Duaz that say just compile this really stripped down version.
If-def small or something.
Yeah, something like that. If-def small, that sounds right. maybe time for one more real quick question, but not much other than that. And otherwise, thank you all for coming.
Small token of appreciation from the
Thank you so much.
organizers.
Thank you, thank you. So, hi. My name's Rob. As you can tell in what you showed up for, global Anycast using OpenBSD on a budget. I'm going to lower the bar in the next like 10 seconds. I've had very little sleep. I'm tired. This is all the content's there. We're good. I'll give you the thing. I just want to make sure people understand. If you have questions, please do ask. If you don't understand something, please do ask. There are going to be people in this room who I talk over, but most of the time I'm probably going to be talking well under people in this room. And it'll be areas of networking that you may not touch on a daily basis or you may not have thought of in that way, but that's kind of generally what I'm aiming for in terms of demographic. So really quickly, what you can expect. So just to be clear, there are numbers on the slides as I fall over myself, but there are slide numbers. There are 45 slides. I'm going to run through them nice and quick. Some of them are going to be very short and very quick. Please tell me if you want me to keep going. So we're going to go over what high availability and reliability downtime stuff is, because that means different things to different people. If we're giving a talk about it, let's all be on the same page about what we're talking about. We got privacy, pricing, and costs, which is basically self-hosting, right? So self-hosting, we'll get into what that is, whether or not, you know. We're going to talk about external networking, BGP and anycasting, talking to other networks. We're going to talk about internal networking, VPNs. We're going to talk about PF-Sync a little bit. We're going to talk about that's not in here, but like routing domains and basic routing. Storage on OpenBSD. And I say that with like lsyncd, Fuse, MinIO, iSCSI, NFS. Different solutions to the same kind of problem, but basically, yeah. We're going to talk a little bit about some software that runs on top of all this stack. So if you're running this kind of an anycasted network and you're using some of those infrastructure systems that exist, you're probably going to be running things similar to this, not this, but similar to this, whether it's Console or CoroSync or Elixir or the Beam or other systems that make use of the clustering. Short of very static CDNs, you're probably going to be running some software that has machines talking to each other. And yeah. We're going to do a very simple demo and example application, as in like, hey, look, it's up, it works right now. I can show you and go through the demo and that kind of stuff. We'll do QA and heckles, but basically if you have any questions during the thing, please do ask. One note about this, Nix on VMM. There was a conversation, there's some people in the room who've been hacking on VMD, and a lot of the issues that I have running this system and playing around with this stem from storage. And they stem from storage, and that's a known thing. That's okay with OpenBSD. We're going to talk about why. We're going to talk about, hey, these are some things that could work. But I want to make something clear. Because you can run Linux inside VMM on OpenBSD, 99% of your problems can be solved that way. And when I say your problems, I mean very specific edge cases where you actually want this piece of software that doesn't work in this operating system right now easily, but you can run it in Linux. You could do the networking on the host such that you are effectively running OpenBSD. There's a little sidecar, effectively, sidecar, depending on who you talk to in Kubernetes or container land, but a VM that is doing some specific things. One of the big things I want to emphasize here is I didn't do that for this talk because it would be trivial to just use Ceph, let's say, or take your pick of other distributed file system, which is 99% of kind of the pain point right now, depending on how you architect the system, depending on what you're trying to do. So we're going to run through some of this stuff. Some of the, overview of the definitions. There are distinctions here. Most of you understand this, but I do want to be clear about what I'm talking about. So availability is you can still use it. That's not the same thing as you're getting packets thrown at your front door, because that's in basically in the face of, that's resilience. So if you have an adverse network condition or you have a power outage in a data center, all those things are very much related and they are going to impact your availability, but availability is specific about being used or obtained. And that's important because when you're talking about anycasting, you can basically say, well, I lost my resilience in a certain area, but I still have availability because you're looking at a macro level. You can say, okay, I still have availability in like 95% of the world, or the 95% of my edge cases that I care about, even if you're having a horrible time over here. Like if Australia goes dark, but everywhere else in the world works, and it's 2 a.m. in Australia and you're like 9 to 5 business, you don't really care. So these definitions kind of matter. And I kind of wanted to just mention this as this is what you need to think about if you're looking at doing any casting or you're looking at doing global networks, because at the end of the day, you're going to have issues. That's okay. It's a question of what are you planning for and how do you talk about it? How do you think about it? Ballpark things, ballpark times, percentages, those are just pulled off of a standard website. These are pretty well known in the industry. Bottom line, your POP is going to fail. Your server is going to go down. That's okay. I mean, you can architect the thing with I've done it, and everybody in this room has done it to some degree or another for different levels. You can architect very reliable systems. You can have multiple power supplies, multiple UPSs. You can make it very reliable such that it's probably not going to go down. You can run systems for about a decade before they go down. Sure, but the thing that people don't really talk about is you still probably have one administrative point that has root to the server. You still probably have one operator who's going to go click and kill it. There's a lot of telecom hardware that has a lot of built-in protections against that kind of environment. Operating systems, generally speaking, don't. I mean, you can run in secure levels and that kind of stuff, so you can get around it in a lot of ways, but you start upping the security levels in OpenBSD, you start to lose some of the functionality that some people want as they use the system. At the end of it all, it doesn't work. So we're going to run through this. You really don't get to control everything. And the biggest thing out of all of this is that single points of failure are administrative in nature. So if you have a machine that can go and SSH into everything and can take it all down, well, that laptop or that key becomes the single point of failure, maybe not the network. Also, there are some things that are not just malicious. Like, this shit happens, and you can't really solve for it. So an Anycast primer, just to make sure everybody's on the same page, because realistically, there's a wide range of audiences here. When you have a subnet on the public internet, you usually advertise it through transit gateways or other larger ISPs. If you go and talk to other people, you can advertise that in multiple locations. If you're advertising the same IP range in multiple locations and you're actually serving the same, you're serving the content out of those networks, then that's generally speaking referred to as anycasting. Generally speaking. But the idea is that, your resolver, your content delivery network and that kind of stuff might be using the same IP address, and depending on where you are in the world, you'll route to somewhere else. Some people will say it's about load balancing. For the love of God, please say no when somebody says that. It's not. Yes, that is the right term. So the comment was load distribution, and it is that. You have no control about where people send traffic to you. At the end of all things, if I'm in Dublin and I have a global network and the local ISP decides to tunnel their traffic and send it to me in Dubai or in Australia, I can't control that. I'm going to take their packet on that end of the network. And so you basically don't think about it as load balancing. Don't think about it as trying to distribute as much as you can, but the big value comes from lowering latency. Because 9 times out of 10, the network's going to be closer to the end person or the eyeball or the server that it's talking about, right? Side effect of this is denial of service mitigation. So professionally, I've seen seriously large volumes of spoofed SYN, and that can take down a machine, that can take down a network pretty easily. It can saturate even some transit links up to 100 gig. I mean, you take a look at people there are published reports of spoofed traffic, volumetric attacks hitting hundreds and hundreds of gig now. And so unless you're pushing 400 gig on your transits, and you have that to spare, you probably need to care about that in some way. Anycasting helps with that because it means that if all that traffic is coming from one location, it's a question of if, but if it's spoofed traffic, there's a decent chance compared to actual legitimate, like, reflected traffic. So that would be, oh, I talked to this DNS server and I spoofed that DNS request. That DNS server comes back and sends that. Then you can distribute that load, right? So you get a whole bunch of DNS servers distributing all that traffic coming back to the target network. That's a distributed system. Whereas if you're doing actual volumetric attacks, it's spoofed traffic, it's spoofed IP addresses, but it's all coming down the same pipe or a specific set of static pipes. And anycasting allows you to mitigate that to a large degree because it means that it's going to hit one or X number of your nodes as opposed to your entire network. And that's useful in some ways. So what I'm trying to solve for, only one single point of failure is administrative in nature. I was trying to build a network so that basically it wasn't going to go down unless I hit a button and did something stupid. And then it becomes a policy question. It becomes an organizational problem. You start to talk about splitting keys. You start to talk about multi-party systems. It gets into the realm of non-technical problem to solve. And it's worth noting that DDoS mitigations, if you're bothering to do this, you do get a reasonable stepping stone into doing proper DDoS, mitigating at the current best practice DDoS mitigations because you're already using the tools that allow you to do the thing in the first place. We're going to talk about, there are two different kinds of things here. We're not talking about the same thing. If you're talking about self-hosting, some people in this room will say it's not self-hosting unless you own the box. Some people will say it's not self-hosting unless you own the server room. Right? It's define that. And then there's going to be some people who are like, well, I own AS, I have my own space, and I'm able to run the stuff, so I own it. If you want to take it down, you have to come talk to me, or you have to go talk to a bunch of different providers. So pretty standard stuff, hardware hosting, co-location versus standard, VMs. I think everybody in this room is pretty much on the same page with that. So there's a bunch of places. I'm not going to enumerate them all, but like co-location, fairly straightforward. Go find somewhere to put your hardware. There's a bunch of places all over the world. Depends on where you are. If you're looking for virtual stuff, the reason I got started in this at all came across bgp.services. It is a website. I highly recommend you take a look. There are other lists of this kind of stuff, but these are collated lists of people who will give you KVM slices or VMs. Misha is nice enough to basically work with me to be like, okay, can I do this, please? Maybe. We'll find a way, maybe. But the point is, these are VM providers who are willing to say, okay, I will do BGP with you as well, and I will terminate on that VM. And that means you can spin them up all over the place. There's also a middle ground here. So data packet, CDN77 stuff, that's actually bare metal. It's bare metal as a service. You'll find some content delivery networks, either themselves or a partner organization actually run basically bare metal as a service next to IXs, and you can usually get into them that way. So we're going to run through this quick. 10 slides, I got 30. Yeah, that's good. Okay. So biggest thing out of all this, you're talking about two different things. I did want to mention direct connections. So if you own the hardware and you place some hardware at a decent IX, there's a good chance a public cloud provider is going to allow you for a price to peer with them directly or over the IX fabric. They'll give you different routes, as in like, for the, okay. As an example, one of the providers, this is Vultr in this case, but it doesn't really matter who, is willing to take $1,000 a month and give you a 100 gig direct connection. You can saturate that link all you want. They don't charge for inbound traffic, which means that they're providing you inbound transit at 100 gig. That may be really useful if you have an eyeball network. That may be really useful if you actually want to do a whole lot of scraping and take the fire hose and then do something with it, right? So I thought I'd mention that. From a pricing perspective, you've got some variables on both sides, but the biggest thing is renting compute and network resources. It's going to be very much dependent on what you use and where you go. It will be a monthly cost. You can roll it into your OpEx. And it's fairly cheap to get going. We'll get into pricing in the next slide or two, but like, it's affordable. The unaffordable part is the resources to be able to do the thing. That's the biggest cost right there. And that's if you want to buy it, right? And ballpark, this is not correct. This is accurate-ish at the time. It'll change, but this is all for V4 space too. It's worth noting you can do this all with V6 for much, much lower pricing. And you should. If you're interested in this, you should do it with V6. And again, this is, you know, star, star, star. These resources come with an added cost because you have a yearly annual cost associated with them. And that's basically, yeah, max. That's 18.
1,800
Yeah.
starting next
Yeah.
start now.
Yeah. So yeah, what Max was saying was that for the RIPE region, it's going up to 1,800 euros per year to have an LIR organization. And that's very roughly speaking a /24 and an ASN and the ability to assign those resources.
Although I was checking yesterday, if you want the /24, the waiting list is 1,000 members long, and the first member on the waiting list has been there for 528 days.
Yeah.
So there's no way.
You're going to be buying the resource from somebody else and doing a transfer if you want this in the next 2 years, at least, in RIPE. Meanwhile, you go to Afrinic and you actually legitimately have business in Africa and you're hosting in Africa or you're using resources in Africa and providing internet services, probably not so much of a wait. And this is all for V4. For the love of God, please use V6. You can lease this stuff. So it's worth mentioning, you can, it's an affordable route if you're in the middle stage. So $100 a month, 100 euros a month, on a month-to-month basis is going to be about times that by 2, but it means that you can do like a year out. Your operational's up there, but it's actually affordable to do this if you're interested in it. It's basically leasing out unused V4 space. So on the low end, I put pounds there, or euros there instead of dollar signs, but it is about the same, roughly speaking. Low end compute resources, anywhere from $10 to $25 US dollars, euros-ish, very roughly speaking. This is all go talk to somebody, it'll change over time. You only get charged on egress on the VMs if you're gonna go the route of using VMs and going to talking to all these different providers. That's useful, but watch how much people actually talk to you because you're looking at a 1-to-10 ratio roughly. So a 1-to-10 ratio, if you're getting a whole bunch of traffic in, you're still putting, like if you're taking that fire hose, you're still egressing 1/10 of it. That can add up. On the very low end, $100 or 100 euros gets you a 1U server. It's not gonna be the most powerful, it's not gonna be the most power efficient, but it'll work. Co-location at the very low end, 75, 100, ballpark. It's gonna be more, but you can find that and have it work. It's gonna be about $200, 200 euros, depending on where you are. Again, very dependent, like about 50% dependent as far as that price point goes, depending on where you are and what deal you get. And then your local IX is gonna be roughly anywhere from 100 to, depending on your port, like 500. So we're gonna get into some OpenBSD stuff, thank God. That was a lot of background to give you talk about like what we're talking about with Anycasting. And pricing as to why you might wanna do this because it is affordable and possible. If you're not familiar, our domain, basically you have an interface. It belongs to an R domain. And that basically determines what, when a packet comes in the door on the interface, that determines what routing domain is in. You can have multiple routing domains. You can have the same IP address exist on multiple routing domains. This is useful in certain ways. You also have tables. Tables are forward routing. So basically, yeah, we're just going to keep going because I got 25 minutes. We're going to rush through this shit. Ask me questions afterwards. You can read the slide. There's one R domain for the public stuff, R domain for the VPN endpoints, that kind of stuff. But the idea is you might want to offer a VPN service where you have the same public IP externally as you do for your client, so that when you use a VPN client, you actually get the public IP on that machine. You can do that with R domains. There are other use cases. So, lots of details omitted. I'm going to be very blunt about this. This works, it's fine, but like the big thing is BGP on port 179 and remote access of some kind. These are for like every single node you deploy, right? You're going to have some way to get to it, whether that's a whether that's a WireGuard system or any other VPN or like SSH. And the big thing here about the pass out keep state, start to think about what R domain you're passing out on, because you can start to pass out on different R domains, meaning you might transit it all the way across your network and then out the other side. There may be reasons for that, there may not. So I shouldn't have made these clickies, I'm realizing now. But the basic idea is with BGPD, so BGP, very simply speaking, hey, this is how you get to my stuff. It's not that at all, but you know what? It's for the purposes of this talk, you have a subnet, you want to make that subnet available. BGP is how you do it. OpenBGPD, really great. There's others as well, but OpenBSD has OpenBGPD. It's used a fair bit. There's a reason it's used. Very simply, the configuration looks like that-ish. There's lots of details, there's lots of caveats. But the idea is you say, this is what I'm going to advertise. Then I'll have a permission ACL model similar to PF, similar to other things, allow, deny, and it does the thing. I didn't cover any RPKI or IRR stuff in that, and we're half over, and I'm half over my slides, so I'm making good time, but like there's details here, okay? Please, if you are interested in this, talk to people, do this in a reasonable way. Bogons, communities, and prefix limits exist. Yeah, communities are massive. If you're doing this at scale in a serious way, you're already using communities. And that's how you have to work, because it allows you to, communities for people who don't know, because there will be somebody in this room, it's not just sending, here's how you get to my network. When you send that message, you can specify specific pieces of information as well. And that gets carried along to everybody else in the world. So that the person over in Tokyo, well, there are caveats, but very roughly speaking. So the person in Tokyo sees that bit of information. It can get filtered, it can get modified, it can get translated, but the idea is it allows you to at least try to send out that as well as receive that, and you can act on that. So BGP pipe. Anybody else seen this stuff? BGP pipe at all? Am I talking? Yeah, okay, a couple, two. I got it working for OpenBSD with TCP MD5. Very simple, very quick hack. There's a PR open to start getting it into reasonable. But it is nice. OpenBGPD is a full-fledged, reasonable BGP speaker. BGP pipe is a series of tools that allow you to basically, everything it says up there. It allows you to inline it. It's written in Go. It's half reasonable. It's got some decent usage. It is useful. And it's useful for, inlining and then talking to a BGP speaker, because you can at least see it. You can tap off of it. And because it's in Go, you could literally shove it to a Kafka stream or a RabbitMQ thing or go to MRT, or you can act on the data. You could inject stuff in, and it's all separate from your existing BGP system, which you may or may not want to actually care about very specific production requirements. Also, it can be a quote-unquote poor man's BGP speaker, in the sense of, depending on what you're doing, and you don't need to update the fib, and when I say that, you don't need to, if you're running this, depending on how you set it up, you could run BGP pipe and not open BGPD. It's possible to do that. If that's your use case, it's possible. So I wanted to point this out because it's a big thing. If you get into doing this, or if you're doing this already, most of the time you can do this, and there's reasons to do it, especially when OpenBSD doesn't have the bad, like you can only crank a single core decently fast. You're going to use like some offloading on the NIC, but you're still going to have an issue if you're pushing a couple hundred gig. You're going to load it up with a couple hundred, like 100 gig NIC cards, and you're still going to have an issue on the CPU side. This will allow you to get around that, but still be able to use OpenBSD. Also, that entire problem is exactly the same scale down. If you're not running like seriously high performance offloading, or you're not running decently speeded CPUs, you probably want to consider this if you're a commercial shop, if you're doing serious bandwidth and serious traffic. You also probably have one of these big commercial routers already. So this allows you to add OpenBSD as a speaker without actually buying whole hog into changing your architecture. For the love of God, if you don't need internal routing, don't. I say that because 9 times out of, like, the issues involved are getting around that. So if you've got this network, you've got, say, a dozen nodes or 100 nodes or however many nodes across the globe. Each one of them is going to have a connection to that local internet service provider, right? That local transit provider. Probably multiples. I'm not even getting into the fact that you're probably connected to the IAX and you probably have a bunch of different networks there. But for the very simple make it work situation, you got a single VM, it has a single virtual NIC, and you're talking to an upstream, and they're taking your BGP. And they might be giving you back BGP. Even if that's the case, unless you're statically serving files, or your application is that you don't need any internal state whatsoever, you're probably going to have to backhaul information from a node in Tokyo to a node in New York. And that's only because, hey, the user logged in over here, and suddenly they came up over here. If your model is that you have to have that work, you need to care, right? And a lot of this stuff in the lower half is all about that. It really is. Cool. We're going to run through this nice and quick. I mean, we're going okay on time. But yeah, questions, comments, concerns so far. I've been going through this really quick, I feel like. But at the same time, people aren't nodding off. Yeah?
So the question is, you're using both Cling and IPsec. So you have 2 different VPNs? Or?
Yeah, so thank you. So these were some of the things that I tested out because I was doing this and it was kind of interesting. And Tailscale. Yeah, so there's a bunch of stuff in here. So these are different VPN systems. Tailscale's fine. If you want to just eat the dog food, it works. It'll do the thing. You can run headscale out of OpenBSD, which is basically self-hosted, single tailnet, which is a very fancy way, because for people who don't know, it is very, very roughly speaking equivalent to a WireGuard tunnel with VXLANs on top, packaged up nicely. That is going to offend a bunch of people, but it's accurate-ish. And that basically means that you can create a mesh VPN that's actually half reasonably efficient. That's what that does. Headscale allows you to basically have a management administrative system where you go and say, these are my nodes, you add a node in that system, and that gets pushed down to all the different systems. They actually check in and say, do I need to get somebody new? It uses WireGuard under the hood, and that uses public keys, so there needs to be a mechanism to distribute those public keys. That's what that exists for, right? The reason why I flagged certificates is because it's really nice. You could have a YubiKey or an actual HSM or other systems and sign your shit and sign the certificates that are for each node. Then you could set up each of those nodes to implicitly trust anything that is signed by that CA. That means you don't have to enumerate on each host all the other nodes. And that's really useful. And it avoids the problem of having to copy. It effectively works around the problem of having to copy your SSH key everywhere, very roughly speaking. The other things listed on the bottom of the slide are basically how to shove traffic from one side to the other over a network of some kind, usually encrypted, but some of them aren't encrypted, and you usually layer them on top of each other. It's worth mentioning, I did this ISA KMPD, Ike v1. It defaulted into like triple DES, which was fun to see. So if you're going to use this, use IKED. There's other stuff in here that I'm not talking about. BGP, OSPF, you can do VXLANs, all that stuff. Go talk to a few ISPs in the room. People do this more than I do. I've touched it, I've played with it. Hey, look, it works. But like, there's knowledge in the community, and there's definitely knowledge in your networking community. For the purposes of what I was looking at, I actually ended up using BGP internally as well. The reason for that is I was already running it, and it worked just fine. So it has some nice features for what I wanted to do as well. Basically means that if one node goes down, the other nodes immediately figure that out, as well as can route traffic. Because of my case, they're always routing to my transit provider anyways, right? So even if I'm routing from Tokyo to New York over my network, it's still hitting my transit gateway at one end and popping up my transit gateway at the other, because it's one interface. Like, you can do this really cheap. This was yesterday because I blew up the network and had to rebuild it. But the basic idea is you can have, there's a reason why the full mesh gets out of hand. That was the note on this. If you get to this kind of scale, use a route reflector. A route reflector is basically a one-to-many relationship. So you have all these nodes. They all talk to one or a high availability system or some other system like that. And the routes for all of the other systems get distributed. So it's a one-to-many relationship. It creates a star topology because otherwise you have a full mesh. Anybody do the math on what a full mesh is at even? Yeah, exactly. On like 30 nodes, on 50 nodes, on 100 nodes, it does not scale. You can do it if you have the resources, but it's a stupid way to do it. Yeah, it just gets out of hand, and all you're doing is just keeping these TCP connections back and forth. There's a thing called route reflectors. They exist. Use them if you're going to do this. Also, worth noting, advertising routes isn't everything. You still need to be able to route if you want this state internally. All of this is predicated. This entire thing from like this, basically the third or fourth slide, is predicated on you need state internal to your network or application stack. And you can't just shunt that to another provider. If you don't need that, don't do any of this. Just have a one-to-many distributed system where you just say, push my configuration, push my content, and then have each place do its own thing. So much easier. But I wanted to make the point here that even if you distribute the routes, that doesn't necessarily give you, depending on configuration, that doesn't give you transit. That just says, oh, you said that IP address is over there. Great. You still need to add in a bunch of configuration, whether that's a learning bridge, whether that's like spanning layer 2 and Ethernet IP, which I did because I could, or VXLAN, or take your pick, or any other network systems. PF sync, do you need it? I'm going to go over this again, but like every single time, if you don't have to do anything, don't do it. PF sync is great, but in this kind of environment, you could actually, and what I did just for shits and giggles, was I used PF sync on the forward egress of all these nodes, right? That's a state table that's distributed across the globe. It worked. I'm not saying you should do it. You shouldn't. And that allows you to do, for example, I could have a VPN behind the scenes and actually have it, NAT. I could have a gate, and it would do the thing. It would NAT. I could have an open connection, and I could literally go thunk, that machine goes off, and nothing changes. That was useful and kind of neat. Unless you're running a massive VPN with weird requirements, you probably don't need that. One thing that is reasonable to do, reasonable being relative, is basically change it to a stateless firewall on the front end so that you're firewalling on whatever you're talking to on the other end. So that all the traffic, it means that you're transiting the traffic. So like architecturally speaking, you would end up with traffic passing into your network and then being routed to wherever it was going, like say my laptop if I was a VPN network of some kind, and then it wouldn't be on my laptop, it would be on the connection just before my laptop, as opposed to on the other side, on the egress side. It means it's a little simpler because your laptop is probably only talking to one or two places instead of everything. So we're going to get into storage, which I mentioned was the hardest part of this whole endeavor. LSync D. uses iNotify under the hood in OpenBSD. It batches, basically you change the file system, you have a glob or other file system selectors, batches them up to a reasonable thing, and then fires off an event. You can then hook on that event. So you want to use Let's Encrypt certs on this system. Well, okay, you do it on one side, like say in Tokyo, but then the request to verify that you actually control that domain comes up incoming in, say, New York. You need to be able to serve the file that was the challenge in New York, or at least transit that data, right? Or at least transit that request. LSyncD is pretty useful for that. It's designed specifically to handle this kind of case, low amounts of files. Doesn't scale well. It also doesn't do the full mesh. It doesn't do like high availability in that way, but it does work. Fuse. At some point, I will upgrade my C chops to help contribute to this in OpenBSD. This is the one pain point that I would love to see changed. The reason for it is the version of Fuse that exists in OpenBSD does SSHFS and a few others as far as Fuse goes, and it's amazing, and it works great, and I didn't write it, so I'm not complaining. The thing that I automatically reached for was a Fuse file system to back this onto S3 object storage. The reason being is there's a half dozen different vendors, there's a half dozen different systems out there that'll do that. And for this kind of an application where you want a highly available guaranteed system, you can use erasure coding on that system, and it works. I looked into some really crazy stuff, like writing a Fuse pass-through file system and then just using Raft under the hood. It works, it's fine, it's just kind of crazy. MinIO, S3 compatible, all that stuff, great. I'm going to skip through this stuff because we've got 8 minutes. I'm going to roll through this nice and quick. I want to get time for questions if people have it. So, MinIO is annoying. It has licensing issues. It also requires you to number them. So as an example, there's the zone part of a config file to allow you to do the startup MinIO, because if you don't number them, it refuses to start. iSCSI, block level storage, remote, basically is what amounts to talk to your disk over TCP. You can then pipe that over an IPsec tunnel or other things like that. Works really well. Highly recommend going and checking out that link. It ends up, this is what you can run into so the idea is you run, I'm just gonna skip ahead. See the performance. It can be pretty brutal depending on what you're doing. So that was writing 1 meg of data and it took 50 seconds. Depends on what you're doing there. Depends on how you're doing it. But the basic idea is with iSCSI, you want to create, you've got, say, a bunch of nodes. Each one of them runs iSCSI. That gives you a block on, like a block device on each node. You can then use software RAID on top of that to do a distributed system. And it works. I did it. I did RAID 5 over the Atlantic. It's fine. It's fine. Until it broke. And it didn't break on the RAID 5, by the way. It broke based on the file system, because you ended up having a situation where you have to have a single write onto the file system, because the file system itself. So you've got a guaranteed RAID 5 block storage. That works really well, and that's fine. The issue becomes your file system. You end up having two operating systems that have read-write on a file system pointing to the same file system, same block, and that causes problems. I got around that by using NFS and CARP. Yes, I see people shaking their heads. I agree. This is why I mentioned Fuse. This is why I'm giving the talk. I did this. It works. I don't want to be the person doing this. I just kind of did it because I could and it was fun, but it is worth mentioning that you can do this with OpenBSD. You end up with this, you talk to NFS, which then has high availability because of CARP, which has a single write path into a software RAID device, which then uses iSCSI targets on that to distribute it. But you end up with a single HA file system using OpenBSD only. And it works. So, yeah, there's some, CARP exists. You can set it up however, I'm just gonna keep going because we got time. We did a bunch of that stuff. Getting into CoroSync. There are going to be some mathematicians that are either watching this or in the room. It creates basically It creates mathematical objects that allow you to have a state machine. It guarantees virtual synchronicity. So you can create a state machine and write a program, and that can be distributed. It's how it comes out of DRBD. It also, I've seen some things online where it like got used in like air traffic control, that kind of stuff, where it's like this needs to work. You get some guarantees that way. These days, you're probably not using it. I played around with it a little bit. I wanted to make, yeah, exactly. So it's used in Proxmox. It's used in Asterix as well. So Asterix uses CoroSync under the hood for their guarantees, and that ends up working on your cell phones. But anyways, I got it working. The new things here use something called KNet. Don't. This is a Google slide that I pulled off. That's the documentation. There are people in this room who are just going like, oh God. Basically, it's some guy, wow, it's probably a couple people, who decided, and that block of red is literally what they had. The content in white is their presentation. So they're doing things to get performance in their little special world. CoroSync now by default uses this as the network stack. It deprecated UDP. It technically works, but it deprecated it. So just be aware. Don't use CoroSync for this. It can work. Use it if it's applicable, but 9 times out of 10, you're going to be using something else. Also, it took a while to patch it into OpenBSD, but it worked. I say into in the sense of I got it running, by the way. Console exists. There's a bunch of others that do the same thing. It exists. You can add it. It's used a lot in Kube and a lot of other systems like Nomad. It basically is a service mesh. Spin it up on all the different nodes. They can all talk to each other. It allows you to query them with DNS, let's say, so you have a load balancer somewhere or multiple load balancers. There's a bunch of other things. It can route traffic, all this other shit. Doesn't really matter. Console, Elixir. There are going to be people in this room who know a lot more about Elixir and the Beam than I do. Beam's pretty great. Ran it in prod for a while. Worked on it professionally. It comes out of telecom. The notion is that things should be allowed to fail, and when they fail, you should handle them. And that's really important, and it lends itself very well to an anycasted network where you've got a bunch of distributed systems. So I thought I'd mention that. All right, so we're going to do, there's the, so curl, I've got this anycasted network. So let's just close off these things. So if I'm currently using a commercial VPN provider, fine, easy enough, right? I get this address if I go to that. So I'm querying an anycasted address. If I log into that server, each one of these servers is set up with a single static HTML page which says this is my IP address, just for easy. I can log into this system. Notice I got a different address, except I didn't because I still curled the same address. That's where the value comes in. Think of this, if you want to, it's not correct, but it's close enough, as what multiple A records in DNS does for you. It's not correct, but it's close enough, depending on what level of the stack you operate in. So I just hit a different node. That was the networking that did it for me instead of anything else. Looking glasses are great. I will, and thank you to the people who run this. Basically, multiple looking glasses all merged together gives you a nice thing. But you can see that my network right now is over here. And there are 3 places, 3 different providers. It's worth mentioning that one of these providers, like Vulture, which I mean is just one of X number, has like 4 or 5 different machines on it that are all advertising. But as far as the networks are concerned, it's still one because it's still one provider. So this spans multiple different providers. The goal is do this. If the entire AWS system goes down and I'm using it, it doesn't matter. If the entire, if Amsterdam gets nuked, God forbid, it still works. And more to the point, you can separate this out administratively So it's not just one provider, because that's 9 times out of 10 what's going to happen. It's not going to be a nuke taken out in New York. It's going to be somebody at AWS pushing a config change and it managing to get through. This solves that problem because you actually are HA'd across multiple providers seamlessly. And yeah, that was, oh yeah, and there's lots of GPT shit on the thing. And that's it. All right, I'm done. I'm out of time. Yeah.
Do you have any system, so many Anycast networks, they run checks in the background,
Yeah.
and if anything fails, they stop announcing.
Yeah.
So you have that in place.
For me, no, I was just playing around and doing this, but yeah, I've done it before and it worked. It's fine. Basically, there's 2 methods of thought. There's a really great Nanog presentation done by some people over at WordPress, or whatever their name now, that they did local self-checks as well. So they've got some health checks on the node so that if it gets hammered inbound, maybe you still can't talk out or something like that, but you need to be able to say, oh my God, I've got a problem, and what amounts to shoot yourself in the head for that node, so that the global routing table goes, oh, well, he died, I'm going to go over here. But yeah, you can run checks and health and all that good stuff. Yeah?
You know where you're doing the Anycast,
Sorry.
how do you handle TCP?
I'm
How do you handle TCP, like, you know, where
Yeah.
you know, where there's a routing transition, like,
So there's a bunch of research into it last while. For the most part, it doesn't matter, is the simple answer. So TCP, generally speaking, takes the same path, hits the same node. If you're on a cell phone, that may not be the case, but for the most part, it does. And even on a cell phone, unless I was noticing I was roaming in multiple carriers here in Ireland, but if you're on one carrier, you're probably going to stay to the same IP, because they're probably going to not change their forward routing tables, right? It is a thing, though. Like, if you do change, it's just going to hang up. It's just going to reset, TCP reset it. There are ways with PF Sync to make that not the case, but generally speaking, you're just going to reset it. Yeah, last one, and then I think we got to get going.
Did you evaluate XBGP rather than pipe?
I'm sorry?
Did you evaluate XBGP rather than BGP pipe?
So the question was, did I look at ExaBGP, right? The simple answer is no. I would love to, I probably will. I played around with a bunch of different BGP implementations. I was running OpenBGPD and I went, hey, this would be kind of cool, off-the-shelf stuff. I ended up going there, but I should look at ExaBGP. There are other BGP systems. Please look at them. They all deserve love. All right.
Just a quick clarification. Were you running like BGP on top of WireGuard, for example? Or
Yeah.
So,
Internally, yeah.
okay, so you had like two WireGuard, for example, two WireGuard endpoints, BGP sessions, right?
Yeah.
With them, and then you were redistributing also like other dynamic routing protocols, like for example OSPF.
I wasn't. I didn't have a need for it. But the basic idea is BGP is external. I also used it internally over VPN connections.
Okay.
But
so you had IBGP on your side?
Yeah. I had IBGP on my side.
Never tried to redistribute like a dynamic routing protocol?
No. I did a learning bridging layer 2, because I could, mainly just to annoy my network friends. But anyways, that's a lot of talking. Please come talk to me afterwards. We're done.
Appreciation from the organizers.
Thanks. Appreciate it. I'm going to give you
about the adventures of IP version 6 and OpenBSD.
Well, I suppose with the state of the network here, this is more of a fantasy kind of talk. But yeah, it's about IPv6. You're supposed to introduce yourself. So I'm Florian. I've been an OpenBSD developer for over 10 years. I've added a bunch of stuff and I deleted more stuff. So once the difference ever reaches 0, I will resign. And this year I made it up to 2,047 commits. And this is where this all started in 1999 with the Kame stack merged into OpenBSD. And the Kame project kept on. So this was a Japanese research project. This is all well before my time, and I'm not a historian, but so they eventually shut down in 2006, I think. Code got merged in from that project and also maintained in OpenBSD, but after that there was not a lot of actual development as far as I can see. It was mostly maintenance, making sure that the code still compiles, still works with changes in the network stack, that kind of thing. And well, to be honest, there was also not a great uptake of IPv6, of course. I would say that it changed in recent years. So we saw in the previous presentation how much IPv4 space costs, and people really can't afford anymore to run IPv4, I think. So we need to make sure that IPv6 gets better. I did a bit of work in IPv6. So this is a timeline, but we were more looking at it from a subsystem kind of perspective to make a coherent story out of this. And we're going to look at IPv6 on the edge, because like on your laptop, in your home network, that kind of thing, because in the core or on your server, it's kind of boring. It just works, and it has been working for a long time. It's just that nobody uses it. But you it works the same as IPv4. You configure a static address, you configure a default route, you spin up your server, you're done. It just works. But if nobody's using it, what's the point? And for people to use it, we need to improve things on the laptop, on users' machines, actually. And if you're looking at on your machine, you have IPv6 enabled, and you see maybe 4 addresses there. And the first one is a link local address that can be only used to talk to hosts on the same layer 2 network. The next one is a globally reachable address, which is formed out of a prefix and a key that's on your system. So it kind of looks random. And it is random from the outside, but it will stay the same when you stay on your network. Like you reboot your laptop, you request a new IP address, you will get that IP address. The next one is a temporary address, and that one is completely random. It is valid it stays around for a day, and then it will just disappear, and you get another random one. And we already have another random one, because IPv6 addresses can expire. They have a lifetime. They actually have 2 lifetimes. They have a preferred lifetime, the PL time, which is a 0 for the third address, which is then shown as deprecated, which means you can still use that address for existing communication, but you should not use it for new communication. And that's why we ended up with the 4th address, which is another temporary address, which has a preferred lifetime that is bigger than 0. And you also have a valid lifetime. When an address reaches a valid lifetime of 0, it's invalid and it just disappears. This is like a DHCP lease expired in IPv4. Be quicker. So we have these 4 addresses, and we want to talk to a destination. How do we do that? We need to choose an address, and that is a source address selection. There's, of course, an RFC for this. And now, looking at the code in OpenBSD, there were comments that OpenBSD implements a previous RFC. And then, so the question was, do we actually need to do anything about this? So looking at the new RFC 6724, there are 8 reasonably straightforward rules in there, what we need to do if we want to reach that destination. And these are those rules. So if your destination is on your machine, on your laptop, then just use it as a source. Source and destination is the same. Prefer appropriate scope. So this was about the link local addresses. If you want to reach a link local address, you must use a link local address. You can't use a global address. They can't talk to each other. It does not work. Avoid the deprecated addresses. If you don't have anything else, well, you can still use it. OpenBSD does not implement mobile IP, IPv6, so home addresses is not a thing. We don't care about that. Prefer the outgoing interface. So you can have multiple network interfaces, and before you do a source address selection, we're doing a route lookup. That's how we figure out that packet will go out there. Well, use an IP address that's on that interface. You can have unnumbered interfaces, well, then use another IP, but prefer the one that's on that interface. We don't implement matching labels. It's maybe something I need to look into at some point, so we can ignore that. Then we prefer temporary addresses and use the longest matching prefix, which is a pretty weird one, which you will probably not run into your laptop. So, what the RFC is doing or imagining is you have a pool of IP addresses, which is your candidate set, and you boil this down to 1. So you have your candidate set of, say, you have 2 IP addresses left over, you want to reach the destination, then you just write them underneath each other, and you look, where is the prefix the longest? Well, it will probably not change on the addresses that you have on your laptop because they are all the same prefix, so the length is the same. It doesn't matter, but anyway. Now, if you're looking then at the code, you find this piece of code, and don't try to read the comment. And we are at rule 5 here. After that, we concern ourselves with temporary IPs and with the longest prefix thing. But this is not the code here. So that comes after this comment. So there's this comment which says, oh, yeah, this comes down to 2 cases. There's a lot of words, and then there are even more words. Roughly speaking, oh, this is going great. And then we have a table which lists these weird, like the second line is variables that are calculated in some strange way. And so we're saying the RFC imagined you have a candidate set and you boil this down to 1 IP address. What the actual code does to implement this is it picks 1 IP address. So you don't have any IP address. You pick the first one, and then it iterates over all configured IP addresses, and it compares them. Is the next one, is that better? Then swap them. This is what it asks about replace question mark. And sometimes you need to replace things, and sometimes not. So I'm staring at this table, and I'm staring at the code, and I'm actually doing this for days to figure out, will this ever reach a point where it needs to replace the current best IP address? And I come to the conclusion, no, it does not. There was no case where it would do anything. This is basically that code. And so my theory how this ended up is because of bit rot. So it claimed it implemented this RFC, but looking at the code, it did not have that much to do with the old RFC either. So I figure I know that they wrote the code and the RFCs kind of at the same time, and I suspect that this is some old stuff. And could not really figure this out from any CVS history or that kind of thing. And so eventually I decided, okay, let's just drip this all out and simplify this. And there were no regressions-ish. So it's supposed to do the same thing, and it kind of did. The problem is, you're supposed to arrive at a single IP address at the end, but the age rules don't provide this. You still need a tiebreaker at the end. And the old implementation picked the newest configured address, and the new implementation picked the oldest configured address, but just because the way it was implemented. And this has consequences when with a flash renumbering event, which means that your ISP reboots and gives you new IP addresses, and you're using the old ones, but they are no longer routed. So they're still valid, but the ISP is no longer routing them. The ISP is not supposed to do this, but these things happen. Now, the reason in this change of behavior is because of the data structure that's used to store IP addresses on interfaces, and this is a tail queue. And so it would be easy to get back to the old implementation, basically always swap when things are the same. But that will break if someone ever wanders in and changes this data structure. Like if someone changes this into a simple list, we have the same problem again. So we want something that's independent of the data structure. And what I came up with is compare the lifetimes, which in practice works. You can construct cases where this does not work, but I think those are constructed cases. Now, there are actually 9 rules. And there's rule 5.5, which is preferred addresses in prefixes advertised by the next hop. And then it goes on and says, this is not applicable for if implementations do not track this. And basically, nobody tracks this. But this really got some traction in the OITF recently, where there's a lot of hemming and hawing. We really should do this. It's great. We need this. And people are writing drafts to make this into, you must track this and you must implement this implementation. Or it's probably should. Not entirely sure. And so this is relevant for if you're multi-homing, like a small network, a small office, that kind of thing. If you're your own ISP and you have your own address space, it doesn't matter because you're speaking PGP to the outside and it just works. But if you have, if you're multi-homing your home office, you have 2 ISPs. They give you different addresses. You configure those addresses on your interface, and then you try to reach an outside destination. If you're routing out through ISP A, you must pick an IP address that ISP A gave you. If you use ISP B and route it out through ISP A, they will block this. So that's why you need to track where did this address actually come from. This used to work in IPv4 because everything is netted anyway. So your network uses RFC1918 addresses internally. It routes the packet somewhere to the router of the ISP or well, the CPE on your end. It nets and it goes out. So it does not matter there. Turns out this is pretty easy to implement. We're doing the route lookup anyway, so we have this information, except if you're trying to talk to localhost, there's no need for that, or multicast packets, but most of the time we do the route lookup where it matters. We do have space in the data structures to store the next hop. We can just abuse the space that we have for point-to-point interfaces where we need to store the destination, so we can just put the router in there. And we need to pass this up from userland, which is also easy because, well, we have point-to-point interfaces. We need to already be able to configure this. And the implementation looks like this. So this is, this function does the source address selection. We need to pass in the route structure. We need to check that we actually got one because, well, sometimes we don't have one for like localhost. And when it comes to rule 5.5, we could remove the comment, we do not track this information, because now we do. And then we check, is the IP address that we used actually from that router? And if not, then switch it. Yes?
Does it also work for point-to-multipoint tunnels like MGAE?
Unlikely. The question was, does it work for point-to-multipoint tunnels? And I don't think so. I also don't see how you do Slack on there. So this is concerned with stated address auto-configuration. So I don't think so. Yes, but this is concerned with stated address auto-configuration. So what's going on about, well, you have these IP addresses on your interfaces. Where are they coming from? Well, a router gives them to you by sending an ICMP6 multicast packet called a router advertisement, and this contains the following information. Hey, I'm a default router. You can use this /46 prefix, and I'm glad that PSLA is not here, to form your IP address and hope for the best that you don't collide with anything, which you probably won't, because you have 2 to the power of 64 addresses in there, so that's fine. And hey, there are also some name servers that you can use. On the host side, your client, your laptop, what it then does is it waits for those router advertisements, or it solicits them, and uses the information to configure your system. The old way, as in Kame stuff, was split between kernel and userland. The kernel would listen for the router advertisement and then configure your system. It configures the addresses, it configures the default route. And on userland, we had a thing called RTSOL, which sends out router solicitations. Now, this had some problems. The router advertisements are not necessarily particularly simple packets, and parsing them in the kernel has some security issues because you don't have any privilege separation or stuff like that in there, so that's not cool. And the kernel would just, so it parses them and forms an address, and it would just jam this in. It would just put it onto the interface, which is awkward if you're trying to unlock the networking stuff in the kernel. So it's nicer to have this configured at one point where also all the other addresses come in. On the userland side, RTSOL, again, this old Kame stuff, from the early 2000s, it predates things like Wi-Fi or suspend resume. It imagines you run your desktop, you fire it up in the morning, it sends a router solicitation and waits for advertisement. If none comes, it sends a router solicitation, waits, sends a router solicitation. If nothing comes, it just stops. So if you use it on a modern laptop and you wander to a new Wi-Fi network, it does not do anything. So you don't have IPv6 for 15 minutes, because that's about the time when a new router advertisement comes by anyway. Or you suspend resume your laptop, it doesn't do anything. So the solution for that is rip this all out and move this all to userland. So I wrote SlackD for that. There's an entire presentation at the BSDCon in 2018, I think, about this. So it's privilege separated and it's pledged. So all the good stuff. It's always running. If you don't configure it, it doesn't do anything. And to configure it, you set the autoconf flag on your interface, and it starts to do work. It starts to send router solicitations. It keeps track of the state of your interfaces. Like if your Wi-Fi is roaming, you're moving to a new Wi-Fi network, it notices this, does new router solicitations. Same way for suspend resume, it notices the interface comes back up and it starts to do work. It figures out that on the new network that you showed up, there's actually no IPv6, so it starts to deconfigure the addresses to avoid breakage, which is also kind of important. And yeah, it handles DNS, multiple interfaces, multiple routing domains, all that stuff. Then, so I was saying, there's this thing that sends you router advertisements, and the old and crofty way was router advertisement. And the configuration the man page for the configuration file had this nice tidbit. It obeys the famous termcap file format. Yes, so famous, infamous. I think it's kind of like a flammable and inflammable. They are both bad. So yeah, termcap, like it uses colons as separators, and yeah, that's great for IPv6. So I think what happened there is, like, it's the only parser that was available at the time, so let's just use this. So yeah, this thing needed to go. It was bad. So well, while we're at it and writing privilege separated network daemons, we might as well write another one. How hard can it be? Turns out not that hard. And while we're at it, we bring in a what we refer to as a parse.y based config file. So in parse.y, there's a YAC parser. It has its own lexer in there. And it's the standard way on configuring OpenBSD things. So if you, like HTTPD, PF, your window manager, CWM, uses this, if you use TWM. So if you configure something that does not, when you don't recognize this format, then you stepped into something ancient. So all the stuff basically uses this. And what this does is we configure a bunch of name servers that get advertised. These are outside of the interface blocks, so the interface blocks inherit this, but you can also override this on an interface. And then we configure that we want to send router advertisements on two interfaces, VLAN 42 and VLAN 64. On VLAN 42, we say auto prefix, which means, hey, look at on this interface to figure out what prefix is on there, and then use that to send the advertisements. But this is actually the default, so you can leave that out. And which is what VLAN 64 does. It leaves the auto prefix out, but it sends a NAT64 prefix, and we will talk about that at the end, what that does. You can also configure static addresses on here and give them lifetimes if you want to. But this is about the auto configuration, which we're talking about next. Because now the next question is, where do I get my prefixes from? So you're not your own ISP, you don't have your own address space, so you request the prefixes from your ISP. And you either request a single prefix, or which is big enough to then split up into multiple prefixes for each interface, or you ask for multiple prefixes. And then we use that prefix information that we got from the ISP to configure the interfaces, and RAD picks that up. DHCP-CD from ports can do that, and I had some trouble understanding what the configuration actually means and how to use it, but I kind of got it to work. Now, this being OpenBSD, we of course want this in base. And wanting things in base always has this problem that needs solving. So you need someone who's sufficiently bored. You need someone who has a need to tackle that problem, and that person needs to be able to do something about it. It's always that. And in the past, we actually had, I'm aware of two diffs of where two people were sufficiently bored and they had the means to do something about it, but they didn't have a use. So those diffs went nowhere. They sent them to me, and yeah, cool, run with it, get it in. I'm happy to review it, but well, they don't have a need for this. I did not have a need for this because, well, crappy ISP. And well, then the stars aligned, and because suddenly we had someone who was sufficiently bored, who had a need, and could do something about it. Hi, that was me. Because my ISP rolled out DHCP v6, so cool, let's do something. Turns out the CPE they sent me was just too crappy to develop anything against it. You needed to request just the right thing. If you requested something wrong, it would stop speaking to you. And the only way to get it to speak to you again was a factory reset. Now, once I figured out what I actually needed to ask that thing, it would only answer once. Now, DHCP v6 prefix delegations have a lifetime. You're supposed to renew them. The CPE would not answer. Like, I want to renew this prefix. I don't care. It would the ISP would still route the traffic to me, but yeah, it would not. So it would not answer to the DHCP request anymore. To only get it to answer again is, hey, factory reset. Now the CPE was a critical piece of infrastructure, as in it drove my home office and that of my partner, and so I can't constantly factory reset. That's no way. So I kind of gave up on all this. I thought, I can't make this work. And I thought, and then I noticed something. Turns out I live in the EU. And we had a great keynote that talked about the EU. And one thing that applied to me is, that means I have to, I can bring my own device. My ISP must accept that I bring my own device. So I researched this, and it turns out other people also figured out that this ISP is particularly crappy and their CPE is shit, and hey, use this specific Fritzbox. So I put this up on the one page, and Misha and Ibsen jumped onto this within like an hour. Yeah, we get you that thing. And so I started to implement something. I transmogrified DHCP-LISD and developed this against Kia, which is ISC's DHCP server. I think it does all the things like V4, V6, all that good stuff. And yeah, so I had this running within like a day because it turns out DHCP V6 is not that different from V4. The state machine is slightly different. It has more features, but yeah, it's not that difficult. And so I was mentioning that I had some trouble figuring out what DHCP-CD's config is actually trying to do, and then reading the RFCs and looking what it actually does, it's a thin wrapper around, over the on-wire protocol, kinda-ish. So that was very weird, and so I thought, let's do better than this. And I was actually struggling a bit with this because you need to work out, hey, I want a prefix for these two networks. I need 2/64s for that, which is what this configuration does. I want 2/64s for one for VLAN 42, one for 62. But I need to request the covering one, which in this case is easy. I request a /63. In the general case, this is actually quite difficult, and that is what DHCP-CD sidestepped. It said, well, you do the math yourself and you tell me what you want. And I wanted to do the math in DHCP-6-LISD, and I kind of got this to work. I'm pretty sure there are some maybe weird cases, but I'll skip that. So to figure out what the thing is doing, you can run it in config check mode, and in verbose mode, it will spit back the configuration that you put in. Like, this is what I think you meant. This is what I'm going to do. And so what I then implemented is I put in some comments. So this is what DHCP-6-LISD is actually doing. It puts out the comments and it says, well, from what you told me, I figure I need a 64 for VLAN 42. I need a 64 for VLAN 64. And oh, by the way, you also want to reserve another 57. Cool. The splitting looks like that. And if I do the math to this, the covering prefix for that is a /56. So I suppose you also can now skip installing zipcalc from ports and just use DHCP-6-LISD to. Maybe not. Right, so we have that sorted. We have, like, to recap, we started with a laptop. We want IP addresses. We moved on to the router that needs to handle IP addresses, but the router also needs IP addresses, which gets it from the ISP all the way back to the laptop. So in the beginning, I was saying that IPv6 is kind of really picking up because it just gets too expensive to run v4, and not just because of the address space. It's also the amount of v4 you need in, so I have no idea, I did not look what they're doing here, but so you have a conference network, yes?
They have a huge network allocation, so they give public IPs out.
Right. But yeah, so if you don't have the public IPs, if you do private space, then oh, let's hand out a 24. How many people come here? I don't know. Yeah, 250. No, that's actually not enough because everybody brings a laptop and 2 phones and a tablet. Okay, so this is annoying. So you need that address space. You also need the capacity on your NAT that it can actually handle so many devices, which is all bloody annoying. And if your network is even bigger, it gets worse. So how about we tried to do V6. And so this is a thing that also came out of the ITF, where Jen Nkova from Google was mostly driving this. The idea behind this is we want to, step back. So there is a technology which browsers implement and your handheld devices implement. It's called Happy Eyeballs. What they're doing is, if you have V4 and V6 on your device, they do two connections to your web server or whatever. One over V4, one over V6. They let them race against each other. Whichever comes first back wins, and you're speaking that address family. So if you have misconfigured IPv6, you will never notice this because things will just work fine over V4. So if you then turn off IPv4 and you want to run a V6 only network, everything is broken. So that's annoying. So people don't do that. To get around this is, how about we let devices opt into this? And this is where the mostly comes in. So the network still provides IPv4 for the devices that can't do this, but a device that thinks, hey, I can do this, opts in via an DHCP v4 option. It tells the network, hey, I don't need a lease. And the router hands back a pref64 option in the router advertisement. And that was the NAT64 prefix in the RAD configuration, which does this. Well, that's not what I thought. Where am I going with this? Oh, no, actually, I'm kind of done with this slide. So, now, you have that, oh, no, now I know what I wanted to mention about this. Many devices do this. Android, iPhone do this, macOS does this, Windows does this. So the only device that we're missing here, or the only OS that we're missing that runs on like laptops and that kind of things is OpenBSD, because I mean Linux on the desktop. So yeah, I totally wanted to implement that. So the way this works is you still need to be able to talk to IPv4 things sometimes. So for example, I had two examples. One is, I'm not going to mention that, and the other one is GitHub. So GitHub is v4 only. So if you have a v6 only network, you can't reach that. So that's annoying. The other thing is, there are things that use address literals or that fundamentally request an address family. So I can give an example for both, which is a ping. So you ping an IP address. So you ping quad 8, that's IPv4. There's no way around it. You can't magically upgrade this to IPv6. Well, turns out you can. By tunneling it out of your IPv6 only network to the edge, which can be your router, or it can tunnel through your whole network. So if you're an ISP, you can run your whole ISP network with multiple hops IPv6 only, and only at the edge you do address translation. And this works because IPv6 addresses are quite big. There is a lot of space where you can fit the whole IPv4 internet in there. So you only need the /69 and 96. So this is a well-known prefix. So since the addresses are 128 bits and you need a 96 plus 32 is 128, so this fits perfectly. So what you're doing is you encode the IPv4 destination in the last 32 bits, send it on to a thing that runs the NAT64 translation. So it notices, oh, this is this well-known prefix. Let's drag the v4 addresses out again, do some network address translation, and send it on. On the return, it does the opposite. Now, that's on the server side, or that's what is referred to as the provider side translator. On the client side, the PF rule, so PF kind of can do this. The rule is massively more complicated. And there's a reason for that. So for starters, you need to set up the IPv6 address dynamically, because there's no way in PF to say, hey, pick the global address on that interface and put it in there as the from. That's not a thing. So if you're saying interface :0 for INET6, that's not what this gives you. It will give you link local address. So this is not going to work. Which means we need a daemon that sets this up. And I wrote another privileged separated network daemon because that's all I do. And I called it GelatoD as a nod to Michael Lucas, and who really likes gelato. And I claim if you squint just right, then gelato, gelat kind of sounds right. I really should not name things. Yes. So, and this whole thing is in ports because the configuration for this is massively convoluted, and Andrew gave a talk about how we don't like convoluted things. We want things just working, and this is the opposite of just working. And the reason for this complication is that AF2 only works on incoming rules. But on the client, when you send a packet out, you need a pass out rule because you don't see the packet going into the network stack. It only goes out of the interface. So what this configuration does is it sets up two pair interfaces, puts one into a different routing domain. The traffic enters a pair 1 because that's where the default route, IPv4 default routes to points through there to the other end. It then enters our domain 1 where it is an incoming. So this packet is coming in on pair 2. And then we can do all the rewrite magic and punt it back to our domain 0 and send it out. This is, I don't know, Todd Freeze kind of crazy, but it works. So yeah, this kind of needs improving. And what I looked into is, can I remove the pass-in limitation from AF2? And so I looked at the code and where this came from, and I think the limitation comes from because this AF2 is a transmogrified route 2. Where this is actually true. So the comment says this only works on incoming rules because we are doing a route lookup. So we already did the route lookup, so we can't do it on a pass out rule because we can't change the routing table, the routing information anymore. This is not actually true for AF2. I hacked around in this and I got ISCMP working-ish. It's a bit weird, and UDP definitely works. TCP is horribly broken, and the server side is also now broken. So that's not cool. The thing is that on the client side, we technically don't need stateful rewriting. The RFC actually says that this is a stateless rewriting. So, I mean, in OpenBSD we kind of don't care because we run PF anyway, and it does stateful, so we might as well do that. But maybe it's easier to not do this in PF, but do it the macOS way, where they have an extra IP address on the interface, the last IP address. And they configure the NAT64 prefix. It's kind of a typo here, but anyway. And then they do this just stateless. I'm looking forward to Alexander Bloom's talk tomorrow, who will explain to me how a packet traverses the network stack so that I can actually implement this and can figure this out. I think I need IP input for this, maybe. But yeah, that's all I have for you. And we have 5 minutes for questions. Yes, please.
Do you actually need the address on pair 1, or could you use an interface next hop route instead of an indirect IP-based next hop?
I did not fully catch that. Can you?
The Gelato D configuration example, do you need actually the .1 address, or could you just use an interface address as the interface route as your default address?
I think you need it. Sorry?
Wouldn't it be enough to set eFace or EFA?
Yes, but then that's.
You need the source address, of course, but do you need the destination address?
I think you need it for the routing table, but not 100% sure.
Okay, quick question. Just the stateless auto config, you were saying that you play the kind of the lotto, that you don't collide with someone else.
Yes.
Is there any reason why you don't do, let's say, the IPv6 equivalent of an ARP? You know, like, is there anyone host using this?
Oh, yes, of course. Sorry. Also, I realized I should repeat the question for the stream, I guess. The question was. Do I actually have an example for this? No, I don't have this in my slides. Do I? Well,
you made the comment just
yeah, I just made the comment. I can go to slide 2 where it was slide 4. So the question was, so I made the comment that you get handed a /64 and form an IP address out of that and hope for the best. And then the question was, why don't you just probe if that IP address is already used? Like send an ARP request. In IPv6, this would be a neighbor discovery. Yes, and that's actually what happens. There's a thing called duplicate address detection, which does exactly that. So you chose an address, you configure it on the interface, and then the kernel sends out a neighbor solicitation. Hey, I want to talk to this IP address that I'm about to configure. Is anybody out there? And if nothing comes back, then that IP address gets chosen. And slackd notices this if this happens, that the IP address does not get configured. And so I was talking about that this IP address looks random, but it's static. What actually happens is if a collision is detected, there is a counter in there, and that counter gets incremented by 1. So your IP address is not counted up 1, but this IP address is formed out of a hash. So you put in a prefix, you put in a key, and a counter. The counter starts at 0. Hashes this is the IP address. If there's a collision, increase the counter to 1, hash it again. It's completely random somewhere else. So your chances increase that there's no collision. This is attackable by always answering, yes, that's my IP address. So if No, I think so. The question is, you don't, because I think because I made that comment, this is attackable by always saying, hey, that's me. You see, the comment was, so you don't want to do this on the router. No, I think the correct answer to that is you must trust your layer 2 network. If you can't trust your layer network, then you have lost. There are too many attacks against IPv6 if you can mess around with a layer 2 network. And it's the same with IPv4. Like, it gets really difficult.
Those DHCP servers also sometimes test if the IP is taken, even though so you could just respond or before sort of empty the user state.
Yeah. Yes, Paul.
First off, I wanted to thank you for DHCP 6 lease. We very much appreciate that. Thanks. But I wanted to ask, you mentioned to prefer temporary addresses for ongoing connections.
Yes.
That breaks long-living connections.
Yes.
So if you use SSH from your machine and you use IPv6, have your machine running for a day, suddenly your connection stops working.
Yes, type faster. No.
No. If you are using the connection, it still breaks because the address becomes invalid.
No, my joke was about, oh, you're logging into a machine and configure it. Well, don't take longer than a day to configure your machine. No, but no, you chose your source IP address. Like SSH, I think it's -B, I think, maybe. So you can tell it to use this source IP.
For SSH, this is a solved thing indeed, but for other long-lived connections,
yeah. You also wanted to jump in, Max?
Actually, on Mac OS, it keeps the connection open. Well, it keeps the address in temporary.
If it's in use
if
by
it's in use by any session.
Oh, yeah.
You will get actually a new one that is still temporary, and the other one will become deprecated, but you still have it. It won't be used for new outgoing connections, but the ones you have already established, they're kept and it works.
Yes, but that's how preferred lifetime works. I had interpreted this as the valid lifetime.
Yes, so the valid lifetime expires. On OpenBSD, the connection just stalls.
But on Mac OS, the behavior is different. It just keeps it on. So in the office, you're at the NCC, you have V6, you will notice you get a bunch of addresses by the end of the day.
This is actually something that I want to test because, I need to repeat this. So the argument was if the VL time goes to 0, then on OpenBSD your connection will drop because that address gets deconfigured, and on macOS that address is still being used because you have an you use that address. That seems like a violation of an RC. Like you're kind of not supposed to do that. But when, looks like something I want to look at, yes. Yes?
Is there any plans to write or to port i36 to the OpenBSD instead of having people using the HTTP CD instead? Because every time someone goes in DHCP for i36, you have to pull in the HTTP CD from the port tree.
I'm not entirely sure if I catch this. Was this about DHCP server that hands you IP addresses?
Yes, it's about, so there's two DHCP servers.
Yes.
You've got DHCP, which is OpenBSD's, and you've got DHCP CD, which is from the port tree. Is there any plans to have IPv6 support in DHCPD so that you can use a single daemon instead of using both?
Not currently because of the 3 problems, as in, yes, I'm capable, but I don't have a need. And it would not end up in DHCPD because that's old and crafty, and no, this would be a new writing. But it's probably not massively complicated. I think I'm getting kicked out here.
Let's thank our speaker, and this is a small token of appreciation from the
Thank you.